Online students, can you hear me clearly? Online students, can you hear me clearly? Please confirm with a message. Okay, let's start the class. So today we have to continue with properties of matter. Ideally, we'll try to, for sure we can't finish everything today. But it's not a very lengthy lesson. So as a result, we'll be able to finish almost like maybe 50% of the syllabus today. Okay, we'll be able and let's try to finish 50% of the syllabus today. Okay, that is the plan for today ideally. Uh, so starting with the first part, elasticity. Okay, hope online students can hear me clearly. And Mali, write the tunes in the Zoom chat and the WhatsApp group. Uh, so talking about elasticity, okay, talking about elasticity, let's first figure out what is behind elasticity. Okay, let's try to figure out what is behind elasticity. And ideally, the sessions would happen this week and next week. There were two sessions on Wednesday, same thing we did, and today, next week also the same plan, Wednesday and Friday. But if possible, if you are joining today, try to continue for next Friday. Okay. Anyways, classes would be parallel, but won't be 100% parallel. So if you are joining today, ideally it's better if you can join not next Wednesday, next Friday. Okay. Ideally try to have that plan because I'll try to keep the classes parallel, but it's not 100% guaranteed that the classes will be parallel. Okay. That is the issue. So, like talking about the elasticity first part, that means properties of matter lesson consists of three parts. One is elasticity, the second one is viscosity, the third one is surface tension. Okay, so we are starting with the first part, elasticity. Before elasticity, let's think what cause elasticity. Let's think about what cause elasticity. What is behind elasticity? uh, the reason, if we check for the reason behind elasticity, what we have is deformation. Clear? If we check for the reason behind elasticity, what we have is deformation. That means if you take an object, okay, if you take an any object like a liquid, not ideally liquids, let's start with solids. If you take any solid, okay, if you take any solid, maybe a stick, a cube, a cuboid, anything, uh, every system doesn't like deformations, right? Again, in a way, it's one of the ways that nature implement inertia. In a way, it's another method that nature implements inertia. Okay, that means any system would not like deformations. What are deformations? Deformations are like the change of the shape of an object. Okay, deformation is a change of a shape of an object. Clear? That means if you take a system, okay, if you take a system, there can be multiple methods of deformations. There can be multiple methods of deformations. That means one is one-dimensional deformation. One is one-dimensional deformation. That means you place it like this and you apply a force and change the length. You apply a force and change the length of the object. Clear? These are one-dimensional deformations. Clear? These are one-dimensional deformations. You apply a force and change the length of the system. Clear? These are one-dimensional deformation. Then sometimes there's an object like this. You apply one or a set of forces and try to change the area of the object. You apply one or several forces and try to change the area of the object. Clear? You try to change the area of the object. Clear? These we call two-dimensional deformations. Clear? These we call two-dimensional deformations. Okay? You take the area and you change the area. Okay? You change the area. These we call two-dimensional deformations. Okay? Two-dimensional deformations. Then the next example, you take a volume. You take a volume. You take a volume, apply a certain set of pressures, apply a certain set of pressure on the object, apply a certain set of pressure on the object, and you try to change the volume of the object. Okay? And you try to change the volume of the object. We call this three-dimensional deformation. Okay? We call this three-dimensional deformation. And the next thing is, I think even here, like around 60%, 70% of the class have previously taken the recordings of properties of matter and are already done with properties of matter. So I think there are people like that here too. If you did properties of matter previously through recordings, okay, just like it's okay to do like whatever you need. If something is different from the, I think when you ask for recordings, what we provide is 25 batch recordings. If I do something different, if I do something more than like if I do something more than the 25 batch, I'll let you know. Okay? So the students who already got the recordings of the 25 batch properties of matter, majority of the class got that actually. So the students who got the recordings of the properties of matter and already watched them, it's okay to do whatever you need. Okay? It's okay to do whatever you need, maybe a past paper book, do something. Okay? And I'll let you know if I'm doing something important, or if I'm doing something additionally to the 25 batch. Okay? Thank you. Okay? That is the idea for the people who got the recordings. And at the same time, this time also a lot of students. Okay, now you are in a holiday. Now you are in a holiday and you have early. So definitely this should match with your capacity. But if you are okay, like we are doing properties of matter here, but majority of the class already did properties of matter through recordings. And even in this time, a lot of students requested for matter and radiation recordings. Like that, if you feel like you have additional time, you have, I mean, anyways, I'm going to do like even for one student, I'm going to do the keep doing the classes in the main class. Okay, no worries about that. I'll complete every lesson in the main class. Okay, and within 3 months you are done with the syllabus. Definitely I'm going to do that. But if you have additional time, okay, if you feel like you have additional time, just request for recordings of matter and radiation, because it's also an independent lesson. You can entirely watch the lesson without any issue, without any impact from the other parts. Okay, clear? So if you have time, just request for recordings like that and keep watching them. Okay, then when I'm doing the matter and radiation in the class, you can decide to join or not join the class, or else you can come to the class and just do whatever you need and like like focus when I mention that I'm doing a important part. Okay, so that should be the plan for the students who already got the recordings. Okay, because the majority of the students already watched the recordings, and this holiday also majority of the students asked for matter and radiation recordings. Okay, same thing can be done by everyone. Okay, so if you feel like you have time, if you have additional time, okay, just request for the recordings of matter and radiation. I'll provide that. Okay, but the thing is like it should match your capacity. Okay, it should match your capacity. That means we are already doing 2 lessons. Okay, we are already doing 2 lessons. So every week, if you if you feel like you have additional time, you have strength and time to do an additional lesson, just request for the recordings and finish 1 or 2 lessons before that. Don't gonna do that with, I mean, some students asked me whether they should do current, electricity, electronics lessons like that. Request for the recordings of that too. I don't think that it is suitable. Okay, the reason is we are finishing the syllabus within 3-4 months. Okay, 3 months. So then we have 5 months for the exam, right? After finishing the syllabus, we have 5 months for the exam. Uh, so that is an ideal plan to do. Okay, if you rush very important lessons like current, electricity, and electronics, get the recordings and quickly watch everything for the sake of finishing the syllabus. It's a problem, as I see. Okay, it's a problem because you won't grasp the concepts. Okay, I mean, were a lot of students who joined the 24 batch classes from 25 batch classes from 26 batch. But like you already know, you tend to forget stuff, right? So like that's not required. Okay, don't try to watch the recordings of current, electricity, tronic, and all and finish everything so fast. It will be too fast. Okay, it will be too fast, so that you won't grasp the concepts. When you get the set of recordings, what you do is just watch them just for the sake of finishing the lesson, right? Then you are in trouble. Okay, but matter and radiation lessons, it's like just 3 videos. Properties of matter, just 3 videos. This kind of stuff you can easily watch the recording and finish everything. Okay, it's very easy to do that. Okay, it's very easy to do that. That's why. But don't try that for other lessons. Okay, finishing syllabus 5 months before the exam is more than enough. Okay, it feels like an ideal plan. Okay, okay, so let's continue. So there are one-dimensional deformations, two-dimensional deformations, and three-dimensional deformations. Clear? 3 types of deformations. Okay, one-dimensional, two-dimensional, and three-dimensional. then uh, then the force which acts against these deformations, okay, force that acts against these deformations, we called elasticity or elastic forces. Okay, that means we have discussed this when we were discussing mechanics too. The particles of an object, okay, particles of an object would stay at an ideal distance. In any solid object, particles would stay at an ideal distance from each other. What is the meaning of an ideal distance? You know that any particle is made of positive charges and electron clouds. Clear? Positive charge and electron clouds. Okay, that means positively charged nucleus and negatively charged electron clouds. Okay, then the next particles also positively charged nucleus and negatively charged electron clouds. Okay, these stuff can't get too close. These stuff can't get too far from each other. Okay, these stuff can't get too close or can't get too far from each other. Why? If you go too far away, this positive and negative will attract each other. This positive and negative will attract each other. Clear? Clear? They will attract each other. Like, and at the same time, if you try to bring them really close, if you try to bring them really close, if you try to bring them really close, this negative cloud and negative cloud will repel each other. Positive nucleus and positive nucleus will repel each other. Clear? Positive nucleus and positive nucleus will repel each other, and negative cloud and negative cloud will repel each other, right? Then again, you can't get them too close. Okay, you can't get them too close and you can't move them too far. Okay, at the same time. Got the idea? So these particles, any particle have their own ideal distance to stay. Okay, okay. So as a result, any solid object will be placed in a way that its particles are at an ideal distance. Its particles are at an ideal distance. Clear? Okay. They will stay in a way like this. Okay. Uh, so if I draw a graph, okay, if I draw a graph, the force between them, the force between them, the force between them with the distance at this r naught, the forces between them will be zero. That means that is the ideal distance. Clear? There are attractive forces and repulsive forces, but everything will be cancelled out, and at r naught you will have a zero force between particles. That means they are stable. Okay. But if you try to bring them closer to each other, the force between them will increase, and if you try to bring them really close, this nucleus and nucleus will get very close to each other. They will create a very strong force against each other, right? They will create a very strong force against each other. Clear? An extremely strong force against each other. Okay. ah so the force will rise to infinity if you try to bring them really close. But if you like try to pull them apart, if you try to pull them apart, the distance between them may increase. When the distance between them increases, again the force will increase, but now the force is in opposite direction, right? When you try to bring them closer to each other, force is in this direction. When you try to move them away from each other, force is in this direction. That's why it's going in negative direction, right? The direction of the force may change. Clear? The direction of the force may change, but after a certain point, this may again start reducing. Why? I mean, after a certain distance, if you somehow pull the system apart, the system will break down, right? Okay. System will try to provide a maximum force as possible and to replace them in their previous positions. But if you somehow provide enough force and rip them apart, okay, then this force may disappear, right, when the distance increases. Okay. Why? The particles in this table are attracting each other, but if you cut the table into two parts, then the force between them disappears, right? They are not like magnets. They don't try to stay with each other when you cut them apart, right? So when you keep increasing the distance, the force will try to pull them back. Okay. Force will try to pull them back. That's why we have a negatively increasing force, but then the force may disappear. Okay. When the distance increases a lot, again the force will decrease and it may disappear. Okay. Force will decrease and it may disappear. Okay. So this force against the deformations we call the elastic force. Okay. This force against deformations we call elastic force. That means if this is the system, okay, if you provide a force and change its length, or if you provide a force and try to increase its length, against this, a force will act inside this. Okay. A force will act inside this against this force. Clear? And this scenario also, a force will act against this in this direction. Clear? These forces against deformations we call elastic forces. Clear? These forces against deformation we call elastic forces. Okay. Clear? That's no issue with the uh, online students, right? You can see everything clearly now, right? Okay. So this is the idea. Okay. These are elastic forces. So to quantify this, okay, now the main requirement in physics is quantifying natural behaviors, right? That is actually physics, okay? Quantifying natural behaviors, okay? Is everything clear up to this point? Now we need to generalize things to quantify stuff, okay? What is the meaning of generalizing things? That means like something like this. You anyways know that if you have two objects like this, same material, same height and same everything, but the overall force you need to shrink these, and I mean overall force you need to contract this by 1 centimeter is different from the overall force you need to contract this one, right? Clear? The force you need for this is different from the force you need for this, right? Definitely changes with the dimensions, right? When the area increases, the amount of force you should apply changes. Okay? Clear? Clear? Ah. Then again, the for a given force, the change in length of this object, delta L, or I'll call that x, is different from the for the same force, the change in length of this guy, right? Clear? For a given force, if you apply 10 newtons on this object, the x value of it will be different from the x value of this, will be different from the x value of this, okay? It will be different from the x value of this, okay? If you apply the same force on this, clear? If you apply the same force on this, got the idea? So it entirely depends on the dimensions, right? It entirely depends on the dimensions, okay? It's not easy at the moment to analyze these things because it depends on the dimensions, clear? Okay, then we can't quantify things when it depends on the dimensions, okay? So what we do is we try to create two general terms. Two general terms. What are the general terms? We try to create two general terms. Okay. What are the general terms? General terms are this: sigma and sigma and epsilon. Sigma means force over area. Sigma means force over area. Clear? Then there are single medium students, right? Yep. Okay. Sigma equals force over area. We call this one stress. ප්‍රත්‍යාබලය. Stress. Okay. ප්‍රත්‍යාබලය කියන්නේ බලය බෙදීම වර්ගඵලය. Stress is what? Force over area. Force over area. මේකට අපි කියනවා ප්‍රත්‍යාබලය කියලා. Force over area. Stress. Why do we introduce this? It's because it's much convenient. Why? The forces depends on the area. I can get rid of this factor by considering the force on unit area. Clear? Then I'll introduce something called epsilon. We call this strain vikriyawa. It is x over initial length. Instead of analyzing the change in length for any object, it changes from the initial length of the object. Instead of analyzing like that, what we do is we analyze the change in length compared to unit length. Clear? Compared to unit length. අපි object එකේ දිගෙන් බෙදලා ගන්නවා. එතකොට මට එන්නේ ඒකක දිගකට දිගේ වෙනසනේ. Then what I get is the change in length per unit length. Clear? What we are doing here is we are generalizing stuff. Okay, we are trying to generalize stuff. Clear? Okay. So now we have two nice terms. You can find the dimensions and all, and everything is anyways included in the tutor. Okay. Now things are much convenient, right? Things are much convenient. Analyzing sigma and epsilon is much convenient because these two are independent from the dimensions of the object, right? Okay. These are independent from the dimensions of the object. වර්ගඵලය දිග ඒව මත රඳා පවතින්නේ නැහැ මේ දෙන්නනේ. Okay. Clear? Then, okay. Then what we do is, okay, like before moving further, there are two terms, tensile stress and tensile strain. ආතන්‍ය ප්‍රත්‍යාබලය සහ ආතන්‍ය වික්‍රියාව. That is the stress and strain that appears when you try to increase the length of an object. The stress and strain against that. Okay. Okay. This is tensile stress and tensile strain. ආතන්‍ය ප්‍රත්‍යාබලය සහ ආතන්‍ය වික්‍රියාව. Then compressive stress and compressive strain means the stress and strain that appears when you try to compress it. Okay. Stress and strain that appears when you try to compress the system. Clear? When you try to compress the system. Clear? Got the idea? Then moving forward, okay, is everything clear up to this point? Yes? Okay. Yeah, first of all, like up to this point, ask if you have any questions and complete your tudes. Mali provide the tude in the Zoom chat again. Complete your tudes. Okay. Everything is included in the tude, so we are not writing anything in the class. Okay. We are not gonna write anything. Okay. So complete your tude. Okay. I'll give time to time. Try to explain things better. Okay, if you need. Okay. So now what we are going to analyze is, okay, now what we are going to do is, we are going to analyze how things behave when we change these two, okay. We are going to analyze how things behave when we change these two. That means we are going to analyze the stress strain curve of a natural object. We are going to analyze the stress strain curve of a natural object. Okay, what is that? What is the stress strain curve? I mean, when I increase the length or decrease the length of an object, the strain changes, right? The strain changes, its x value changes with that strain changes. And what I'm going to do is what I'm going to do is I'm going to analyze how the stress changes with strain. Okay. Okay. So for many natural objects, this is not ideal for everything, but for many natural objects, the graph looks like this. Okay. For many natural objects, the graph looks like this. Okay. And you have to remember the parts of this graph. Okay. From O, we have O, A, B, C, D, E. So just knowing the names of these parts would be enough, but I'll try to explain it with connection of with proper connection of the natural ideas you have. That means I'll try to explain this with a natural example. Okay, take a rubber band. Okay, take a rubber band. Now if you take a rubber band, okay, now if you take a rubber band, you first start pulling the rubber band. Okay, you first start pulling the rubber band. Okay, then the force you feel when you pull the rubber band, the force you feel increases, right? When you pull the rubber band, the force you feel increases, right? Okay, අතර දැන්න බලය වැඩි වෙනවන්නේ. The force you feel increases when you pull the rubber band. Clear? It's proportional until a certain point. Okay, that we call the proportionality limit. Proportional limit means the stress is proportional to the strain. Okay, then when you increase the length of the rubber band after a certain point, when you increase the length of the rubber band after a certain point, okay, what happens is you pass this elastic limit after a certain point. What is elastic limit? This is the proportional limit, this is the elastic limit. That means you know that if you stretch a rubber band a bit and release it, it will return to the initial length. You stretch the rubber band again, it returns to the initial length. Clear? But if you stretch the rubber band too much, it would return, but not to the exact initial length. Clear? Its length will be increased a bit, right? If you stretch a rubber band a bit and release, it will return to the initial length. If you stretch the rubber band again a bit, it will return to the initial length. But if you stretch the rubber band too much, it will not return to the initial length. There will be an additional length remaining. Clear? There will be an additional length remaining. Clear? Clear? So the reason for that is this elastic limit. Any object have an elastic limit. In the elastic limit, if you stretch it and release it, it will return to the initial length. That's the perfect elastic nature. Elastic nature means when you deform, it returns to the initial state. But after point B, we reach the plastic region. We reach the plastic region. මේකට අපි කියනවා සමානුපාතික සීමාව B කියන එකෙන් ප්‍රත්‍යස්ත සීමාව ඉවර වෙනවා. ප්‍රත්‍යස්ත සීමාව පැන්නට පස්සේ අපි යන්නේ සුවිකාර්ය සීමාවට. We reach the plastic region. What is plastic region? A permanent deformation remains. සම්පූර්ණ දිගේ වෙනසක් ඉතුරු වෙනවා. It doesn't return to the initial length. Clear? නැවත ආරම්භක දිගටම එන්නේ නැහැ. Clear? That is the plastic region. So here we have something called the yield point. Yield point means you may feel this a sudden change of graph. That means when you pass the elastic limit, pratyasta සීමාව පැන්නුවාම, when you pass the elastic limit, you will feel a sudden impulse. You feel a sudden, you feel that the object slipped a bit. I mean, this is difficult to explain, and no need to explain actually. Just drawing the graph and knowing the paths is enough according to the syllabus. But I'm trying to make it connected with some practical example so that you have a better understanding. So when you stretch it, okay, even in a rubber band, if you stretch it too much, you will feel a sudden shake. Sudden shake means you will feel like the force provided by the rubber band decreases all of a sudden. It decreases all of a sudden, and with a sudden shake, it tries to break. Not actually break. With a sudden shake, it will provide a deformation. The color of the rubber band changes a bit from orange to yellow. Okay, when you stretch it too much. Okay. That permanent deformation, the point where that permanent deformation happens is this yield point. Okay, yield point. The point where the permanent deformation happens, we call it the yield point. Okay. Avanati lakshya. What is the meaning of this yield point? What is the reason for this permanent deformation? Every object has some kind of a solid structure. Every object has some kind of a solid structure. What happens is, after a certain point, what happens is, they slip on top of each other. Layers slip on top of each other. Suddenly the layers slip on top of each other. Suddenly the formation breaks a bit. Formation breaks a bit. Clear? That is the yield point. After that, when you release the force, it will return. But that deformation occurred due to the slipping of the particles. That remains. Okay, that remains. Clear? That remains anyways. Okay, that's why it becomes plastic now. Okay, that's why it becomes plastic now. Then what happens? Then what happens? Still the object holds, like, okay, still it does not break. Still it does not break. Now you again keep increasing the force. With the force, again the strain increases with strain. And now you reach a maximum force. That is the force where the rubber band starts breaking. That means now you have provided the maximum possible force. Rubber band is providing the maximum possible force as the reaction. If you pass a certain level, you will feel rubber band suddenly stretches out and breaks apart. Clear? Okay. This is that point. This is the breaking stress. This is the breaking stress. Bhedaka pratyaya balaya, breaking stress. When you reach this stress, okay, things will start breaking apart, and it will be automatically stretched a bit and will break down at this point. This is the breaking point, Kedaka Lakshya. That means when it starts breaking, it would not break all of a sudden, not like glass. When it starts breaking, when you apply the maximum stress, when it starts breaking, you will see the particles are tearing up, but it will stretch a bit more, then break completely into two parts, right? So this is the breaking stress. After that, it will be stretched a bit, then will break at here. This is the breaking point. Clear? This is the breaking point. Clear? Got the idea? So what we mainly analyze in this syllabus is this proportional part. Okay? මේ සමානුපාතික සීමාව තමයි අපි අධ්‍යයනය කරන්න යන්නේ. පැහැදිලිද? What we mainly analyze is this proportional part in the syllabus. Other parts are difficult to analyze. Okay? Clear? Then again, based on the nature of this curve, the materials can be divided into two types: ductile material and brittle material. Thanya dravya saha bhangura dravya. Ductile and brittle. What is the meaning of that? Ductile means the graphs that behaves like this. That means they show a permanent deformation. That means they have a plastic region. They show a permanent deformation before breaking. Okay. A rubber band shows a permanent deformation before breaking. If this concrete structure, it will not blast all of a sudden, okay, okay, it will show a permanent deformation before breaking, okay. You will see for days if the weight above this is too much, okay. I'm not talking about impulsive scenario like an earthquake. If this floor tries to break down due to too much weight, what will happen is for few days you will see the ceiling going down like this, right? Then only it will break. So this concrete structure we have above us has a permanent deformation before breaking. Steel have a permanent deformation before breaking. Okay, if you take this steel structure, when you provide a force, it will bend first. It will have a permanent deformation first, then only it will break. But take glass, you keep applying a force on glass, you never see a permanent deformation before breaking, all of a sudden it shatters. All of a sudden it shatters, right? Clear? If you take glass, you keep applying a force, it may have a small deformation, but you never see a permanent deformation before breaking, right? You never know when a glass will break down, right? There are very popular scenarios behind this too, okay? Popular accidents, okay? Because there are glass structures in buildings. You never know when it is going to break down. Why? Glass will not bend before breaking, okay? Glass will never have a permanent deformation before breaking, okay? Clear? Ah, these kind of materials we call brittle. These kind of materials we call ductile. ආතන්‍ය ද්‍රව්‍ය සහ බංගුර ද්‍රව්‍ය. So if you take glass, its graph looks like this and its breaking point lies here. Okay? Its graph looks like this and its breaking point lies exactly here. Just after the proportionality limit or the elastic region, it breaks. No plastic region. Clear? ප්‍රත්‍යස්ත සීමා ඉවරෙච්ච ඒක පුපුරනවා. එයාට කවදාවත් සුවිකාර සීමාවක් ඉතුරු වෙන්නේ නැහැ. No plastic region, no permanent deformation, it just shatters. So you never know, okay? You never know. That's what actually happened with Titanic, okay? That's what actually happened in Titanic. I explained this, right? Like the Titanic is not an easy object to break down. Okay, why? Even by a collision of a glacier, okay, even with the collision with the iceberg, still a metal, a very strong metal will only bend, right? It will not shatter. That's the whole property of metal. That's the whole property of steel. That's why we use steel for everything. Okay? Even with a huge impact, okay, there's no way of piercing it. There's no way of breaking it. It just will have a permanent deformation. Okay, so if you hit with a iceberg, you will have a bend like this on the ship, but still the ship should remain. But you know that the Titanic just broke into two pieces and went down, right? It was broken into two pieces and went down. How can that kind of a strong steel structure break into two parts? How's that possible? That kind of a strong steel structure, okay, although we don't see that, it's tons of steel, right? Tons of extremely hard steel. Okay, if it collides with the iceberg, it will stop there, but it should hold, right? How can it shatter? How can it break into parts? Because they were not able to identify this at that stage in those times. Steel has a property, after a certain negative temperature, it converts from ductile to brittle. Steel has a property, after a certain negative temperature, they were going in negative temperatures, after a certain negative temperature, steel turns from ductile to brittle. Okay, so at very negative temperature, steel doesn't have those nice ductile properties anymore. It looks like glass after a certain point. It becomes brittle. Okay, if you cool down steel after a certain negative temperature, you can just put a force, it will break. Clear? You can just give a small impulse, it will break. Clear? That was the issue there. I think in those, I mean, initially we didn't have this problem. I mean, those days, thousands years back, the ships were made of wood, right? Ships were made of wood. The people were traveling peacefully thousands of miles without any issue. Then in the World War seasons, we turned into what? We turned into steel. Then they had this problem. They made the ships from steel. You go to invade a country, a country with a sea with negative temperatures, none of the ships reach the destination, everything breaks on the middle. Okay, thousands of ships were broken in the sea when they enter the negative temperature areas. They didn't know this reason. They thought it was due to attacks, but even for an attack, a ship can sustain, right? Okay, they made these ships, warships, very strong, but all the ships shatter when it reached there. You just need few bullets. Okay, you just need few bullets. Even by a pistol you can get rid of the ship. Okay, you don't need huge weapons. You even with few pistols you can get rid of the ships. Why? After a certain negative temperature, they are not perfect ductile steel anymore. It's like a glass ship. Okay, it's like a glass ship. Okay, now also we are making things with steel, but now we have the capacity to alter the properties of steel. Okay, now we are capable of altering the properties of steel, so we now don't have that problem. Now if we collide with a glacier, we have the capacity to break the glacier and go through this. Okay, not very hard glaciers. Okay, for very hard glaciers they have ice breaking ships going in front of the main ship. You have the main ship, in front of that you have another ship which is capable of breaking the ice. Okay, but even if you collide with something, nowadays ships won't feel that. Okay, nowadays ships won't feel that. There will be a permanent bruise, that's all. Okay, okay, there will be a permanent bruise, something like this on the ship. If it collides with a glacier, that's all, nothing more than that. Okay, still you won't even care, you will reach the destination. Okay, clear? Because now we have altered the properties. Okay, so that's why Titanic was very strong. It was never meant to break down, but they didn't know that part of physics. Okay, that was the problem there. Okay, clear? So ductile and brittle. That's why for manufacturing we always use ductile materials, because you know when it is going to shatter. Okay, you know when it is going to break down. Clear? That's the whole point of using ductile material in construction. Clear? Then let's move forward. Let's move forward. Next, we have to quantify things. Next, we have to quantify things. Proper Hooke's law, we tell that in the proportionality region, sigma is proportional to epsilon. That means in the proportionality region, you already saw that, right? In the proportionality region, stress and strain is proportional, right? In the proportionality region, stress and strain is proportional. ප්‍රත්‍යවලය වික්‍රියාවට සමානුපාතිකයි. Clear? And this proportionality constant we call elastic coefficient. We call this the elastic coefficient. Clear? We call this elastic coefficient. Okay, or elastic module. Okay, pratyastata mapanke, elastic modulus. What is elastic modulus? It's the proportionality constant here, but this elastic modulus term is a much general term. Sometimes there are linear deformations, bends. Okay, sometimes area related deformations, different deformations you have, right? You have different deformations, right? Sometimes you change the volume, sometimes you change the area, sometimes you change the length, sometimes you bend. Okay, okay, there are different types of deformations. Okay, then you have different stress values, different strains. Okay, so the common name given for this proportionality constant is elastic modulus, pratyastata mapanke. Clear? But in our syllabus for questions, what we analyze is only one-dimensional deformations. Only one-dimensional deformations we analyze, okay? So for one-dimensional deformations, okay? For one-dimensional deformations, we give the term Young's modulus in place of elastic modulus, clear? So elastic modulus is the common term given for all categories. When it is a one-dimensional deformation, we call that the Young's modulus, Yammapanke, clear? So when it is bending, we will give another term. When we are changing the volume, we will give another term. For one-dimensional deformation, elastic modulus is Young's modulus, okay? ඒකමාන විරූපණ වලට ප්‍රත්‍යස්ථා මාපාංකය තමයි යම් මාපාංකය කියන්නේ. Clear? Clear? Okay. So actually you know this, okay? This entirely depends on the material, okay? This entirely depends on the type of the material, okay? But you can expand this, okay? You can expand this. What is this? F over area, force over area. This is X over L, right? This is X over L. Clear? Then you do this. F equals gamma. You take A here over L. Gamma A over L into X. Clear? Gamma A over L into X. You take gamma, you take A here and put everything here. And you have seen this before. You have seen this before. What is this? F equals Kx. F equals Kx. You have seen this, right? So elasticity is not actually a new lesson. It's just we have expanded K. This we call spring constant, right? Spring constant K. This depends on the length of the object, area of the object, type of the object, a lot of stuff. In this lesson, what we are doing is we are analyzing F equals Kx. But we dig deep into K. That's all. So this is not a new lesson, just a part of mechanics actually. We are just analyzing the behavior of K. So you get the same set of questions, same kind of questions, just like the questions you used F equals Kx. But now, instead of giving K, they sometimes give you the Young's modulus, area and length. Okay, that's all. There's nothing new in the lesson actually. Clear? Clear? Ah. Let's go for some questions. Exercise 1, question 2. Some questions they ask for the energy. Sometimes they ask for the energy. I'll explain that later. But you actually know, okay? Half kx squared. Can you remember? You actually know how to find the energy. It is half kx squared, okay? It's half kx squared. And you know k, okay? I'll teach that properly, okay? I'll teach that properly. But for some questions, they ask energy. Don't worry about that. Apply half kx squared, okay? So, exercise 1, question 2. Question 3. Question 13. Question 13. If you're done with those questions, just finish other questions too, okay? Because this is not actually a not a new physics part, right? You know half kx squared, you know f equals kx, you know everything, right? Just in this question, what happens is they give information about k. That's all, okay? They just give a bunch of information about k, that's all. Exercise 1, question 2. When an object is tied with a rubber band and hung, its length increases by 10 centimeters. This object is placed on a surface with a friction coefficient of 0.6. Exercise 1, question 2. Object is tied with a rubber band and hung. The length increases by 10 centimeters. So when unnecessary, don't write gamma x, gamma ax over the equation, okay? Just write f equals kx, okay? Here it's unnecessary to write the whole equation. Just go with f equals kx, right? Why? In the question, they talk nothing about the initial length. They talk nothing about the area. They talk nothing about the Young's modulus. So it's just a mechanics question, okay? So object tied with a rubber band and hung, its length increased by 10 centimeters. That means if the spring constant is k, you hang this mg, then the force in this is again should be equal to mg for equilibrium. So F equals kx, F equals kx, F equals mg equals kx, kx. So k equals m, g means 10 over x, x, what is x? What is x? 10 centimeters, increased by 10 centimeters, that means 0.1 meters. 0.1 meters, which means 100 m. Now the question is quite easy. What you do is, when pulled at a uniform velocity. So now you pull the object, you place the object on the ground and pull by the string with a uniform velocity. What is the friction? What is the friction here? You can find the friction. How? The weight of the object is mg, then the normal reaction is r, and r is equal to mg, then the friction is equal to mu r. Clear? Friction is equal to mu r. Clear? Friction coefficient into r. Friction is 0.6, mu is 0.6, mu is given as 0.6, mu is given as 0.6, r is mg, r is mg, mg, g means 10, g means 10, right? Mu mg, which gives me 6m, right? 6m. This is the friction. F equals mu r. This is the friction. Friction is 6m, right? So uh, now you can get the answer. You can get the answer. If it is going with a constant velocity, if it is going with a constant velocity, that means force equals friction, right? Constant velocity means forward force equals friction, right? Constant velocity means forward force equals friction. Clear? What is the forward force? F. What is the forward force? F. F means kx. F means kx equals friction. So what is k? 100 m. K is 100 m. Here you have x. Then the friction is, what is the friction value? 6m. Friction is 6m. Then m cancels out. X is 6 over 100 meters. 6 over 100 meters means 6 centimeters, right? 6 over 100 meters means 6 centimeters, right? So the extension would be 6 centimeters. Okay, the questions are simple like this. Okay, clear? I'll just do the next part only. Okay, what is the increase in string length when pulled at 4 meters per second squared? Acceleration again. Object here, friction 6m. Forward, you have the force, which is equal to kx. Now the system is accelerating. Now the system is accelerating. Uh, System is accelerating at a rate of 4. System is accelerating at a rate of 4. So you apply F equals ma. You apply F equals ma. Here you have kx. Here you have kx minus 6m. You have kx minus 6m. Clear? You have kx minus 6m equals ma. Ma acceleration is 4. Then kx is 10m. Kx is 10m. So x is 10m, 10m over, what is k? What is k? K is 100m. K is 100m. M cancels out. 10 over 100 meters means 10 centimeters. I'm not going to do the next part. Okay. The questions are quite easy. Okay. What is the next question number I asked you to try? You just keep trying other questions. Okay. You don't have to worry about listening. Okay. These questions are not difficult. For someone who's good at mechanics, not a big deal, right? Okay. Things are easy. What is the next question number I asked you to try? Third one. Okay, let's move to third one. I mean, this time also A levels paper is easy. Okay, A levels paper is easy in the sense, I always tell this. I mean, the paper is easy and the marking scheme is terribly hard. But the problem is you don't know when the paper is easy. Only issue is you don't know that you screwed up until the results are out. Okay, that is the only difference. Because papers are, I mean, anyways, in A levels, anyways, the papers are same. Okay, I mean, anyways, like the number of students who get to the university is same, number of A results they expect is same. They change the value of A, value of B, value of C accordingly. So anyways the outcome is same, right? Anyways the outcome is same. We don't have new universities, so anyways the same number of students would go to the university. Okay, but the problem is when the paper is really easy, you identify that only when you get the results. Okay, that's the only difference. Okay, you think you wrote the paper very well. If the paper is difficult, you get the direct feedback. Okay, you start working for the second shot directly. Okay, but when the paper is really easy, you think that you wrote the paper better. But the problem is when the results are out, then the real problem begins. You have to start all over. Okay, so so getting easy papers are not a very good thing actually. Okay, and the problem with easy papers are you have to be really thorough with theory. Okay, one student messaged me, he has done 5, I mean lot of students have done 5 essay questions. I'm talking about good students actually, because only the good students message you immediately after the paper. Okay, others don't message. Okay, so just, I mean, lot of students have done 5 essay questions, not 4. One student has done an additional question just because he has forgotten the paths of the curve of this elasticity curve. Okay, like very small they are really good at maths parts. They are really good at handling any difficult questions. Lot of students My 25 batch is really small, a small batch of extremely good students. Okay, at 26, 27, we can't guarantee that because the batches are big. Okay, it's around 215, 26, around 600 in the 27. So I don't know what is happening with all 600. Okay, I have no idea about in the 27 batch. I have no idea about what is happening with all the 600 students. I have no clarity. But 25 batch, I have an absolute clarity about everyone. So the people are really good, but people are really good at extremely difficult questions. Okay, sometimes they forget to think about small theory parts. Okay, that's the main problem with them. Okay, but no worries, they anyways have more than enough time to do additional questions, so no worries about that. But like what you in A levels, we prepare for a lot of difficult questions. We are capable of analyzing any hard question, but in A levels when you go there, what matters is very small theory terms sometimes. Okay, very small theory terms. Clear? It is really important to know theory very well. Okay, I received a lot of 49, 48s, 47s for MCQs. And one student, he was in top 10 of Ananda College continuously. The he has like he has made like 6 careless mistakes in the MCQ. Okay, so 44, 6 careless mistakes. And another student, I said that 49 MCQs, one careless mistake. The careless mistake is there's a FT graph or something like that. When he take the area, he has forgotten that he need to divide it by 2 when we are taking the area of a triangle. Okay, 49 MCQs out of 50 uh, has forgotten to divide by 2 when taking the area of a triangle. Those are the kind of stuff happens in A levels. Okay, not the very complex kind of stuff. Okay, okay. And the student who said that he went for the fifth question because he forgot the yeah forgot the elasticity curve parts, was continuously in at least top 5 Royal College continuously, section top 5 or top 10. So these are the kind of mistakes happens in A levels. Okay, not the kind of mistakes that we expect. Okay, we expect to get, I mean, in our, my paper 2019 A level paper, the story was different. Okay, in 2019 paper, you know that you are done. Okay, after the paper, you know that. Okay, but there are careless mistakes doesn't matter anymore. Okay, in 2019 paper, because the paper is difficult. Okay, anyways the capable people will be able to do the question. Out of them only the people who do the paper make careless mistakes, right? Okay, people who can do the paper can make careless mistakes, others anyways can't, right? So when the paper is difficult, that is the scenario. Okay, careless mistakes doesn't matter. Why? Anyways the others are not capable of handling the question, you are capable of handling the question, so you maybe do 60% of the question and 40% you lose due to the careless mistakes, but no worries, others are not able to start the question. Okay, so when the paper is difficult, it's really good for good students. Why? You anyways handle everything smoothly, one or two careless mistakes you make doesn't matter anymore. Okay, but the paper, when the paper is easy, then the real problems begin. Okay, then the real problems begin. Okay, then you have to be extremely careful. Okay, here, so it's a different story. Okay, it's a different story. How are you handling a difficult paper and how are you handling an easy paper? Okay, you have to be ready for both. If the panel changes all of a sudden, you get an extremely difficult paper. Okay, you have to be ready for that too, and you have to be ready for an extremely easy paper too. Okay, and in easy papers, these are the things I mentioned are the kind of mistakes you do. Okay, not the kind of mistakes you expect to do. Okay, in A levels you think, okay, I'll get some hard questions, I won't be able to analyze them. Okay, like that, but you go there and you make mistakes. You forget to divide the area of a triangle by 2. You forget to like you do, you all of a sudden forget whether the pressure is a vector or a scalar. Okay, okay, like that those are the kind of mistakes you do at A levels. Okay, not the kind of mistakes you think that you will do at A levels. So still one of any of these doesn't matter for those people. Okay, why? 49 MCQs is really good mark. Okay, anyways. Okay, yes, you missed 50 by a stupid mistake, but still it's 49. Okay, so no big issue. But if you make few of that for that person, the person who made 5 careless mistakes, it's a huge issue. Why? Five careless MCQs means your district rank will go down by at least 80. Okay, your island rank will go down by at least 400. Okay, 5 careless mistakes you can't afford. Even with that one careless mistake, that person's district rank may go down by 5, island rank may go down by 10. Okay, even with that one careless mistake, not dividing the area of a triangle by 2. Okay, so you have to be careful. Okay. Uh, Question 3. Define stress strain and Young's modulus. Stress, force over area, strain, change in length over initial length, Young's modulus. Ah. So what is the definition of Young's modulus? These are the kind of mistakes you make at A levels. What is the definition of Young's modulus? It is stress over strain. It's stress over strain. Young's modulus is stress over strain when under tensile law compressive force. Under tensile law compressive force. You miss that part, you lose marks in A levels. Okay, that's how it is. Why? These are the kind of mistakes you make in A levels. Okay, common term sigma over epsilon. Common stress over strain means elastic modulus. Okay, that's why I mentioned this content. Okay, now you should focus properly on theory points. Okay, okay, clear? So elasticity, okay, elastic modulus is stress over strain. Okay, clear? What is Young's modulus? This is elastic modulus. What is Young's modulus? Stress over strain under compressive or tensile forces. That means one dimensional stuff. Okay, clear? See, you miss those terms, you miss marks. Okay, you miss those terms, you miss marks. That's the problem in A levels. Okay, why? Uh, the whole paper is easy. Everything can be handled. There's one theory question that decides who's getting A or who's getting B. That theory question, they assign 6-7 marks. Okay, I mean, if I ask you to do one simple thing, write the definition of work. Write the definition of work. Quickly do write, if possible. Write the definition of work. I mean, nothing related to the lesson, just checking. I mean, now these are quite important because this is the A-level season. You should understand the nature of the paper. You should understand the nature of the marking scheme. Write the definition of work, because these are the kind of stuff that comes in handy in A levels, not the complex maths. Okay, some students are good at integrating, differentiating, applying quadratic equations, do whatever the things and getting answers in extremely difficult questions. But in the A level paper, they ask the definition of work. Okay, what is the definition of work written properly with the proper equation maybe? මොකක්ද කාර්යයේ අර්ථ දැක්වීම වෙන්නේ? Work is force into displacement, right? බලය වැඩි කිරීම විස්ථාපනය. But force into displacement of the point of action of the force uh, in the direction of displacement, or force into, oh එහෙම කිව්ව නම් ඇති. Okay, force work is force into displacement of the point of action of the force towards the direction of the force. Clear? Got the idea? බලය වැඩි කිරීම, බලයේ ක්‍රියා ලක්ෂය, බලයේ දිශාවට ගමන් කළ දුර. Clear? එහෙම නැත්නම් ඒක අනිත් පැත්ත. Force into, I mean, if I write this like, what is the meaning of the whole definition? What is the meaning of the whole definition? You apply a force here, okay? Then the object moves like this. Object moves like this. This is the displacement of the center of gravity. They give this in A levels. This is the displacement of the point of action. These are different, see? But when writing work, you should write in all other physics in the syllabus. Displacement means displacement of the point of action, okay? In all other physics in the syllabus, for everything else in our physics syllabus, displacement means displacement of the point of action, okay? Sorry, displacement of the center of gravity. In motion equations, in conservation of momentum, when you are writing MGH, in all the scenarios, displacement means displacement of the center of gravity of the object. But only in the definition of work, only in the definition of work means force into not the displacement of the center of gravity of the object, displacement of the point of action of the object, okay? Displacement of the point of action of the object, okay? These are the kind of theory points you miss in A levels, okay? Things that you entirely neglect, okay? Things that you entirely neglect, okay? You don't even care about these definitions properly. Those are the kind of issues that appear in A levels, okay? And the main issue is you write answers very well. When they ask the definition of work, you write force into displacement and you think you will get marks. Then when results are out, then only you figure out that you have to do second try, okay? So be good at theory, okay? Be good at theory. Properly read theory. Properly remember theory. Every word in a definition matters, okay? Every word in a definition matters, because if the paper is really easy, one word can take your, like, shift your district rank by 40-50 points, okay? Clear? So let's move forward. These are the definitions, okay? These are the definitions. Now I think you have a proper understanding about how you should study definitions, right? Okay, it's complex, okay, and you should focus it on it more than doing thousands of questions, okay? Proper understanding of definitions matters, okay? So question 3, uh, the length of a metal wire is 4 meters. The length of a metal wire is 4 meters. Cross sectional area 1 into 10 to the power 3. Cross sectional area 1 into 10 to the power, cross sectional area 1 into 10 to the power minus 3 centimeter squared, centimeter squared. When you hang when you hang 4 kilogram load, 4 kilogram load means 40 newtons. That means when the force is 40 newtons, the extension is 2 millimeters. Extension is 2 millimeters. Extension is 2 millimeters. Okay. So now F over area equals Young's modulus into X over L. Okay. This is the equation. Stress, strain, Young's modulus. So the Young's modulus they are asking, right? Are they asking for the Young's modulus? Yes, right? So you get FL over AX, FL over AX. What is the force? What is the force? Force is 40 newtons. Force is 40 newtons. Length 4 meters. Length 4 meters. Area 1 into 10 to the power minus 3. 1 into 10 to the power minus 3 centimeter squared converted into meter squared 10 to the power minus 4. Then X length, change in length. What is the change in length? Change in length is 2 millimeters. Change in length is 2 millimeters. Okay. Use all this and you get the answer. Okay. Change in length is 2 millimeters. That is the Young's modulus. Is it better to watch recordings of 27 for mechanics or join revision? Depends on the person, okay? Even although I mentioned that a lot of students ask for properties of matter recordings, and a lot of students have watched that, there's a bunch of students, at least a set of students left because they can't watch recordings, right? Okay, so same scenario, like some students can handle recording, some can't. Okay, if you can't handle recordings, if you are not capable of watching a 3 hour recording continuously, if you don't have that capacity, I mean, don't start watching recordings. Then you will watch a 3 hour recording for 6 hours. Just a waste of time, right? Okay. If you don't have the capacity of watching recordings at least 3 hours straight, don't start watching recordings. Join classes, because otherwise you will watch a 3 hour recording at least 5 hours. So if you watch 50 hours of recordings, you will waste around 30-50 hours, right? It's too much. Okay, it's too much. So don't do that. But if you are capable of handling recordings, then yes, go for recordings. This time revision plans are not yet certain from my side, but there will be few revision plans too. Okay, we'll let you know. But at the moment, my main target is finishing the syllabus within 3 months. Okay, finishing the syllabus within 3 months, and we are on the target, so no big issue there. Okay, question. Question 13. Question 13. Anyone still writing this? Anyone? What matters is like don't mix things up. Okay. I mean, what students do is now you didn't do mechanics very well. Now you are like doing things to a certain level. Now all of a sudden revision classes are starting. You give up these classes and go to revision. Now you were doing very well in the last few lessons. Now you have no idea because now you are thinking about joining the revision. Now you try to manage things through the revision. Now all of a sudden you lose track. Why? There's too much of work. Now you were doing the last few lessons properly. Now you are not doing that. Now you started doing mechanics. Now all of a sudden now you know that it's 8 months to finish the whole syllabus. Now again problem starts. Okay, just be neat. Okay, okay, be neat. Okay, that's all. Be neat with your plans. Okay. So question 13, the 3 legs. A table, 3 legs. This is quite easy. One leg, one leg. The problem is it's 0.5 millimeter longer. Length is 75 millimeters. Length is 75 millimeters. That means 750 millimeters. But one leg has an additional length of 0.15 millimeters. You need to get rid of this 0.15 millimeters. So what you do is you place some kind of a weight. They are asking the weight you should place, right? Or the force. Force. You apply a vertical force above this, okay? You apply a vertical force above this to get rid of this additional 0.15. Quite easy, right? So what you do is F equals Young's modulus, take an area here, x over L. What is the Young's modulus here? What is the Young's modulus? 1 into 10 to the power 10. 1 into 10 to the power 10. What is the area? What is the area? 15 centimeter squared. Area 15 centimeters squared. X 0.15 millimeters. X 0.15 millimeters. Original length, this, right? 750.15, right? Total length is 750.15. You have to get rid of this 0.15. Then A gamma. Clear? Clear? Okay. And this is in millimeters, this is in millimeters, so I don't have to worry about conversions. Okay. Both are in millimeters, so I don't have to worry about conversions. Okay. Well, calculator. Do we have the answer, anyone? Because I need to give you another question through this. How to give another question through this. Thank you. Okay. One into 10 to the power 15. You get roughly 3000. Okay, almost 3000. You get almost 3000 newtons. Okay. Okay. Clear? I'll give another question for you to try at home. This is not a big deal because you are applying the force directly on this leg. Same question. Same question. You have 3 legs. Length between 2 legs is 2 meters. Symmetrical system. And again, just like in this question, just like they have mentioned in this question, uh, just like in this scenario, uh, one length of one leg is 750 millimeters. One has additional length of 0.15 millimeters. Okay. Clear? 3000 newtons load means 300 kilograms. We are giving you 800 kilograms. We are giving you 800 kilograms. Where should you please place 800 kilograms to make the table flat? Got the idea? It's a quite difficult question. Okay. Why? If I gave you 300 kilograms, what you do is you just directly place it on the longer one, right? Then the whole force is felt by that guy. Clear? If I give you 300 kilograms, you directly place it above this guy. Okay. No big issue. But when I give you 800 kilograms, it is too much. So you should place somewhere like this. It will change the length of this, length of this, length of this, all three. But I should place it a bit towards this guy so that it will be compressed with this additional value too. Then the table will be flat. Where to place this? A center of gravity question, okay? Where to place this? Just a question to try at home, okay? Clear? It's a nice question, okay? It's a nice question. Let's move forward with the theory parts. I'll finish the remaining theory parts of elasticity. Okay, let's move forward. I mean, these are just theory parts repeating, okay? Only this part, okay? Only this part that I'm going to discuss now, uh, like students who haven't done heat may find hard, okay? Only this part, a very small part there. That part you will find hard if you haven't done heat. This thing I explained in heat, I'm just re-explaining this, okay? I'm just explaining this again, that's all. Which is like forces due to expansions, okay? Forces due to expansions. Can you remember we did this at heat? When we were doing this in heat lesson, I said that I will explain this properly when we are doing properties of matter, right? Clear? So the length, let's take as L. Length, let's take as L. When we increase the temperature of this is a construction scenario, okay? You have two fixed structures in this side. then you have a beam. What happens when you increase the temperature? When you increase the temperature, beam tends to expand, right? This is the way we are going to do the question, okay? Assume that we are increasing the temperature by theta. Then the new length of this would be, L 1 plus alpha theta, right? L 1 plus alpha theta, right? So I take this as my beam now, okay? I take this as my beam. Now I'm going to find how much of a force I should apply on this guy to shrink it and put it into this. That is the compressive force felt by the on this beam, and the reaction compressive force felt on the walls by the beam. Clear? I'm taking this as the initial length and I'm thinking about compressing it and putting it here. Clear? So I would write F equals Young's modulus A x over L. So Young's modulus area x. What is the change in length? This should be the change in length. This should be the change in length, which is L plus L alpha theta, L plus L alpha theta, L plus L alpha theta minus L L plus L alpha theta minus L. That is the change in length. You get L alpha theta. You get L alpha theta. Clear? So the change in length is L alpha theta, then divided by L. Clear? Then what happens? Not actually L, okay? Sorry, not actually L. What is the initial length? This is the initial length, okay? Now in this scenario, this is the length before compressing. That is the natural length of the object, right? Okay, so I should put that here, L 1 plus alpha theta. Then L and L cancels out. You have the force appear as YA alpha theta 1 plus alpha theta. In this case, we can forget this part, okay? Why? Usually these are construction practical scenarios, so we are not increasing the temperature by 100 or 1000 or anything like that. Temperature values are changing by 5 degrees, 2 degrees, 1 degrees, okay? Very small temperature differences. And when you take the linear expansivity, Rekhiya Prasaranatavaya, when you take the linear expansivity of solids, these are really small values, right? 1 into 10 to the power minus 5, 1 into 10 to the power minus 6, 1 into 10 to the power minus 3. So this is a very small value, right? This is a very small value alpha theta, so I can forget alpha theta, okay? So 1 plus alpha theta is almost equal to 1. 1 plus alpha theta is almost equal to 1. Clear? So as a result, you have phi a alpha theta directly. Same equation holds when expanding and when shrinking. Okay? Same equation holds. Okay? You get the same equation y gamma a alpha theta. Clear? Clear? Then the next thing is, you know that the curve of a fx graph, that means curve of a spring is this, right? This is f equals kx in the proportionality region. Okay? Clear? So if I stretch a string from a certain length, if I stretch a string from its natural length to x, what is the work done by me? What is the work done by me? What is the work done by me? It's at natural length and I'm applying a force F and I stretch it by a distance of x. Clear? I stretch it by a distance of x. Clear? So according to F equals kx, when the force is F1, displacement will be x1, right? And the work done is the total area of the fx curve, right? That we know, right? Total area of a force displacement curve gives me the work, right? Total area of a force displacement curve gives me the work, right? Area of fx curve is work, right? Area of fx curve is work. So what is the work here then? Half f1 x1, right? half f1 x1. Clear? Half f1 x1. This is work, right? Clear? Then if you like, you can write half. Instead of f1, I can write f1 equals kx1, right? So instead of f1, I can write kx1. Then another x1 here. Then you get half k x1 squared. You get half k x1 squared. Okay. So that's all. Okay. This is the energy stored in a object when you stretch it. Okay. We call this elastic potential energy, right? Now if you need, you can expand k. Okay. What is k? Gamma a over L, right? Clear? Clear? Now if you need, you can expand k. Got the idea? But sometimes instead of this, you get a stress strain curve. Sometimes instead of this, you get a stress strain curve. What is the area of a stress strain curve? What is the area of a stress strain curve? Area of a stress strain curve is half. I'll take the area as a dash, half sigma epsilon, right? Area of a stress strain curve is half sigma epsilon, right? Clear? Half stress into strain. Clear? What is stress? Force over area. What is strain? X over L. Clear? Stress, force over area, strain, X over L. Clear? Clear? Then what do you get here? What do you get here? You get half Fx. You get half Fx over AL. You get half Fx over AL. Clear? What is half Fx? Half Fx is the energy stored, elastic potential energy of the object. Clear? Half Fx is the elastic potential energy of the object. Clear? What is AL? Area into length gives you the volume. Area into length gives you the volume. Clear? So by the area of a stress strain curve, you get the energy stored in unit volume. Clear? You get energy stored in unit volume by the area of a stress strain curve. Clear? Okay. So next, what we had to do is just questions. Okay, because the major parts are over actually. Major theory parts of elasticity is over. These are very small lessons. Exercise 1, question 17. Question 10. Five. Well, 15. Okay. So you can take the interval now and finish the questions. Okay. I'll start around 10:30. Okay. Try to be here before 10:30 and start doing the set of questions. Okay. Start doing the questions. We are almost done with the all the important theory parts of elasticity. Okay. After the exercise, we have a small out of syllabus part. Okay. Then we are done with the elasticity lesson. Then today we can move to viscosity too. Try these questions. Okay. Keep trying the questions. Keep doing the questions and skip if you can't figure out one question, skip that and move to the next one. Question 17. The catapult is made of two rubber bands 20 centimeter long and 10 millimeter in cross-sectional area. The two rubber bands are pulled in length of 24 centimeter each, projecting a stone of 50 grams. Calculate the maximum speed. I mean, the formation of the rubber bands, how are they formed, what is the placement, we don't have to think about that. Just apply conservation of energy, okay? Just apply conservation of energy. That means you stretch the rubber band, that means you create a elastic potential energy of half kx squared. And there are two rubber bands like that. This overall energy, elastic potential energy, converts into kinetic energy, right? This overall elastic potential energy converts into kinetic energy, okay? So that's the idea, okay? So don't think about the formation, how it's formed, how are they placed. We don't have to think about that. Just a simple conversion. So uh, half K means gamma A over L, right? Now we know the expansion. So K can be written as, what is gamma? Gamma in this question is 5 into 10 to the power 8. Gamma is 5 into 10 to the power 8. Gamma. A, what is the area? What is the area? Uh, area is 10 millimeter squared cross-sectional area. 10, 10 millimeter squared means 10 into 10 to the power minus 6, right? 10 millimeter squared means 10 into 10 to the power minus 6. Gamma A over L. What is the initial length of the rubber band? 20 centimeter long. 20 centimeter long. Then we stretch it. We stretch it until it is 24, right? We stretch it until it is 24. That means the extension is 4 centimeters. Extension is 4 centimeters. Extension is 4 centimeters and squared into 2. Extension is 4 centimeters squared into 2 equals half mv squared equals half m. M means mass. What is the mass? 50 grams. 50 grams means 0.05 kilograms into v squared. You solve this, you get v, okay? You solve this, you get v. Clear? Next, let's go to question 10. So quite simple questions, okay? Just mechanics questions. Let's go to question 10. Question 10. The radius of a wooden wheel is 501 millimeters. Radius is 501 millimeters. And we have a belt radius 500 millimeters. Belt 500 millimeters. I need to put this belt into this wooden block. So what we usually do is, this is how actually they put frames to wooden cart wheels. Okay. If you have wooden cart wheel, what you do is, you heat the metal frame to a high temperature, then it will expand, then it will expand, then you put it around this, then you let it cool down. Then what happens? When it cools down, it tries to reach to the initial length. When it cools down, it tries to reach to the initial length. So it will properly catch the, it will properly and tightly catch the wheel. Okay. It will tightly catch the cart wheel. Okay. That is the idea. Okay. That is the idea. So, so next one is, so minimum temperature at which the belt is heated to fit the wheel. So you know that from heat lesson, you know that you actually like don't have to consider about, okay, you actually don't have to worry or consider about like what happens in a circular way, what happens to the area. You don't have to worry about that. You actually can apply linear expansion laws just for the radius itself, right? Can you remember? Okay, you don't have to think about how the area increases, how the volume increases. No, you can simply apply uh, expansion equations just for the radius only. Okay, clear? So let's apply for the radius. I can write delta L equals L naught alpha theta, right? So delta L means change in radius, which is 1 millimeter. Original radius 500 millimeters. You had to increase it until 501. Alpha, alpha linear expansivity. What is linear expansivity? Linear expansivity is 5 into 10 to the power minus 6. 5 into 10 to the power minus 6 theta. You solve this, you get the value of theta, right? You solve this and you get the value of theta. Clear? Clear? Then extension occurs in the iron belt. So you can get it by the change in overall length, circumference. So the change in length is, or the extension, I can call it x. X is 2 pi r minus 2 pi r naught, right? 2 pi r minus 2 pi r naught, right? You start at 500, you stop at 501, right? So the change in length is 2 pi r minus r naught. You get 2. Pi means 3.14. R minus R naught means 501, 501 minus 500. 501 minus 500 millimeters, 10 to the power minus 3. Millimeters, that means 10 to the power minus 3. You solve this, you get the change in length, okay? Clear? You solve this, you get the change in length. That may needed for the other part, so let's solve that. 2 pi into 1 into 10 to the power minus 3. 2 pi 1 into 10 to the power minus 3. You get 0. C. You get 0.2 pi 1 10 to the power minus 3. You get 0.0063 meters. 0.0063 meters. Okay. There's a question online. Okay, it's solved. It's already solved. 0.0063 meters. That is the change in length. Change in length. Then next one, if the thickness of the belt is 5 millimeters, tension on the belt. So now we know the extension of the belt, okay? Now we know the extension of the belt. If the thickness of the belt is 5 millimeters, if the thickness of the belt is 5 millimeters, that means it's like this, right? That means it's like this. Now they have given me the width of the belt, right? Width of the belt is equal to the width of the tire, width of the cart wheel. There's a width to the cart wheel, which is width of the cart wheel is uh, 20 millimeter, right? Width of the cart wheel is 20 millimeters. So that is the width. And now they are giving me the thickness of the belt. So the belt going around it would look like this. It has a width of 20 millimeters and thickness of 5 millimeters. So this will give me the area, right? This will give me the area. Clear? So now I can calculate, okay? Now I can calculate. This will give me the area. So I can calculate F equals gamma A x over L. Gamma A of x over L. What is the Young's modulus here? Young's modulus of the question is uh, question 13, right? No, question 11, right? Sorry, question 10. Young's modulus is 0.7 into 10 to the power 11. 0.7 into 10 to the power 11. This area will hold as the area of the belt, which is 20 into 5. Area of the belt will be 20 into 5. 20 into 5. Since it is millimeter squared, could be written as 10 to the power minus 6. Then the change in length x, this is x, 0.0063. 0.0063. That is the change in length. 0.0063. That is the change in length. Then divided by the initial length. Divided by the initial length. Initial length of the band was this, right? 2 pi r. 2 pi r. That was the initial length of the metal frame. 2 pi r. 2 pi means 3.14. Pi means 3.14. R means 500 millimeters. R means 500 millimeters. Initial length of the band is 2 pi r. Area is this. Young's modulus. Change in length means 2 pi r minus 2 pi r naught. That's all. That's all. You solve this, you get the force. That is the force created inside. That is the force created inside the belt. Okay. It's the tensile force exerted in the belt. Clear? Last part. When the belt and the wheel come to an equilibrium, draw the force diagram of the right half. Draw the force diagram of the right half. So it's like this. If this is the cart wheel, if this is the belt going around that, What actually happen is on the wheel, belt will create a force like this. It will compress the wheel like this. And the belt will feel the reaction. Belt will feel the reaction like this. And the belt will feel the tension inside the belt by the other half of the belt. What actually happens is, due to these compressive forces by the wheel, belt will have an overall force in this direction. Belt will have an overall force in this direction. Why? In these forces, these components cancel out. These components cancel out. You only have these components. You only have these components. So you will have a resultant force of in that direction from the wheel on the metal band. And the inside tension given by the other half of the band will hold this against this force, right? Inside tension given by the other half of the band will hold the band against the compressive force, right? Clear? So this can be considered as a proper diagram. Okay, clear? Write this down. What was the next question number? What was the next question number? 5. Let's go to question 5. Let's go to question 5. Question 5. Two lengths and cross-sectional area of steel and copper wire 4.7, 3.5, 3 into 10 to the power minus 5, 4 into 10 to the power minus 5 respectively. If under a given load, similar extension is shown, find the ratio between Young's modulus. So the question is quite easy. F equals Y A X over L. So the Young's modulus is FL over AX, FL over AX. Young's modulus is FL over AX. So I can write Young's modulus 1 over Young's modulus 2, Young's modulus 1 over Young's modulus 2 equals FL over AX means what is the force? In the given same force. Same force means I can write same F. What is the length? What is the length? 4.7, 3.5, 4.7, 3.5. These are the lengths over AX. Over AX, what is the areas? 3 and 4. 3 to the power minus 5. 4 to the power minus 5 to the power minus 5. X. What is X? X is the change in length. They are talking about similar extensions. Similar extensions means same X. So X cancels out, F cancels out. You solve this, you get the ratio between Young's modulus. Okay. Then the next question, what was the next number? Sorry? What was the next question number? 12. Let's go to question 12. Let's go to question 12. At the end of a rubber band with a cross-sectional area of 0.16 centimeter squared, a metal sphere with mass 1 kilogram is hung. The other end of the rubber band is held with hand, and the metal sphere is rotated in a horizontal circular motion with a constant speed of 1 revolutions per second. If the radius of the circle is 1 meter, then find the extension of the rubber band. So the idea is this: they need us to find the extension of the rubber band. They need us to find the extension of the rubber band. So it's like this. F equals gamma A X over L. So F I can write as M R omega squared centripetal force. This is, we are talking about rotational motion, gamma A X over L. Okay. And this is gamma, this is R. R can be written as R can be written as the length of the wire, right? Okay. I mean ideally. Okay. Ideally initial length is the initial length. Okay. Ideally initial length is the initial length, and the radius of rotation means L plus X. Okay. Initially radius of rotation means L plus X. Okay. Clear? Ideally radius of rotation means L plus X. Clear? Okay. In this case, radius of the rotation means L plus X, but I'm not going to work with L plus X. Why? X is anyways a small value usually, right? I mean, it will be a lot of trouble if I put X here too. Okay. Okay. Ideally, when I'm rotating the system, initial length is L, but now it definitely extends by X. So now the overall length is L plus X, and the radius of rotation would be L plus X. Okay. Radius of rotation would be L plus X. But the problem is, like, although the radius is L plus X, if I put that here, okay, if I put that as the radius here, it's just a lot of trouble, right? Here you have X here, okay. But the thing is, I don't have to worry about that x because compared to L, x is very small, right? So the radius of rotation I can still consider as ml omega squared without issue, right? The radius of the circle is given. Then that means it's question, what is the question number? 12. At a distance of 2 meter and wire is held horizontally. 2 meter long wire is fastened to two fixed points at a distance of 2 meter and the wire is held horizontally. It's a different question, right? Wire is held horizontally. And the other end of the rubber band is held with hand. The metal sphere is rotated in a horizontal circular motion with a constant speed of 1 revolution per second. If the radius of the circle is 1 meter, then the extension of the rubber band. Then the question is not that clear, right? What they are telling in the question is not that clear. It's not like this. They are talking about question 12. They are talking about 1 kilogram end of the rubber band is held with hand. The metal sphere is rotated in a horizontal circular motion. So the metal sphere is moving in a horizontal circular motion. Horizontal circular motion with a constant speed. End of a rubber band with cross-sectional area 0. And a metal sphere of, and the other end of the rubber band is held with hand. So is it like this? I mean, are they talking about a scenario like this, right? Rotating the system like this, right? There's nothing else that I can imagine in this scenario. Okay. So they may be talking about a scenario like this, right? You are not rotating it like this. It's not a horizontal circle. It's not a perfect like. You are just holding it like this. You are just holding like this, it like this, and rotating it like this. Clear? Clear? That has been the plan here, right? So in this case, the weight of the object would be mg. Weight of the object would be mg. Okay. Now I have to go through all this trouble. This is the scenario, right? Is this the scenario you assumed? Everyone else? Yes? Anything else? No, right? Okay. So I didn't read the question well. I thought it's just a horizontal circle like this. No. It's a different scenario. 2 meter long metal wire fastened two fixed points. I have no idea about these two fixed points. Okay. That is the problem. Anyways, let's assume like no point of wasting time on a unclear question. Let's do this one. So still this is clear, right? What is happening? You have a force. You have a force. Clear? You have a force. And the radius of the circle is 1 meter. Radius of the circle is 1 meter. So what is this theta? What is this theta value? Sin theta. Sin theta. Sin theta is 1 over 2. Sin theta is 1 over 2. Sin theta is 1 over 2. So theta is 30. Theta is 30. Clear? Okay. Why? Am I not reading the correct question? Why? What is the problem? Huh? That is a different question then, right? Okay. I have to read the question properly. Okay, okay. Now this is okay, right? This is the scenario, right? No big difference there. At the end of a rubber band with a cross-sectional area 0.16, metal sphere with mass 1 is hung and the other end of the rubber band is held with hand, okay? And the metal sphere is rotated in a horizontal circular motion with a constant speed 1. If the radius of the circle is 1 meter, then find the extension, okay? Radius of the circle is 1 meter. What is the length of the string? It's not given, right? Then this was the question, right? This was the question, right? I was originally in the proper track, right? Okay. Yeah, I was doing it properly, right? Yes, right? This was the plan, right? Yes. Oh, see? Then what is this question? Is it question? It's question 11, right? No, I mean the other question I was reading, mixing with this one. Okay, so it's the same plan, okay? They are not talking about anything else. They are not talking about anything else. Radius of the circle is 1 meter, so definitely the length of the string is also 1 meter, right? Clear? Okay. There's no other way, right? Okay. Definitely, original length of the string is L and the radius of the string is also L. Okay. So now you directly have the answer. You directly have the answer. What is the mass of the object? Properly, let's read question 12. Mass of the object 1 kilogram. 1 kilogram. Radius of the object L. Length of the object radius. Radius of the circle is 1 meter. Radius of the circle is 1 meter. Then what is omega? Omega 1 revolutions per second. 1 revolutions per second means 2 pi radians. 1 revolution means 2 pi radians, right? 1 revolutions per second means 2 pi radians per second. Omega squared equals gamma. What is gamma? Young's modulus 1 into 10 to the 7. 1 into 10 to the power 7. Gamma A. What is the area? What is the area? Uh, area of the cross-sectional area of the string is given as 0.16. Cross-sectional area is given as 0.16 to the power minus 4. To the power minus 4. The length of the wire is also 1 meter then. They are asking for x. Use all this, you get the answer for x. Clear? Use all this, you get the answer for x. I'll skip the next practical and I'll keep all the practicals to the end. Okay? Let's move forward in theory a bit. Clear? Clear? No big deal, right? Clear? Just mechanics question with a new equation, that's all. Okay? Just few mechanics questions with a bunch of new equations. The whole lesson properties of matter looks like that. Okay? Okay. So consider this as a just as a perfectly horizontal circle. Okay. Consider this as a perfectly horizontal circle because ideally this scenario cannot be happen, right? Due to the weight. Okay. Ideally this scenario cannot be happen due to the weight. Then you have to do a lot of work. Okay. Then you have to do a lot of work. Why? Okay. Just consider it as a horizontal circular motion, maybe moving on a table or something like that. Okay. Consider it like that. Okay. This was the question plan, but that's correct. Ideally, like ideally, if it is just hanging, okay, just hanging, you have to do a lot of work, right? If it is just hanging, you have to do a lot of work because the lengths are not given. So you have to create equations for the lengths and all. Okay, that means Ideally, if we go for the previous plan, if it is like this, if it is hanging like this, if it is hanging like this and moving like this, ideally due to the weight, the shape should be this, right? Ideally due to the weight, the shape should be this. So you may have a weight here mg, but the problem is the length is not given. Okay, length is not given. Then in a scenario like this, the radius is given as 1, then you have to find the force. What you could do is you can put theta here, you can put theta here, then you will get f cos theta, then you will get f cos theta equals mg, f cos theta equals mg, and you will get f sin theta, you will get f sin theta in this direction, f sin theta equals mr omega squared, mr omega squared. Then r you know, so you multiply these two and add them, that means f squared sin squared theta plus cos squared theta, you multiply them, you get the square of them and add them, equals m squared r squared omega 4, r squared omega 4 plus g squared plus g squared r squared omega 4 plus g squared, clear? Then sin squared theta plus cos squared theta becomes 1. Sin squared theta cos squared theta becomes 1. Then f becomes square root m r squared omega 4 plus g squared. Okay, you take f like that, you take f like that, that would be the force exerted on this string, clear? Then you get tan theta. Ideally this is not the plan for the question, okay, this is too much. So you divide these two, 2 divided by 1, 2 divided by 1, I'm just mentioning since you asked the question, f sin theta over f cos theta, you divide these two, then you get mr omega squared over mg, and r is 1. Anyways, m cancel out, f cancel out, you get tan theta, you get tan theta, you divide these two, you get tan theta equals r omega squared over g, tan theta equals r omega squared over g. Now you need to find the length of the string, you need to find the length of the string. For that you need sin theta, this is theta, so you need sin theta. So sin theta equals this length is sin theta equals this length is 1 over L, sin theta equals 1 over L. So you know tan theta, in this case tan theta is r omega squared over g, tan theta is r omega squared over g. Then you get the diagonal by applying Pythagoras law, g squared plus r squared omega 4, r squared omega 4 square root. Then from this you get sin theta again. So what is sin theta? Sin theta is 1 over L. From this side sin theta is r omega squared over this one square root g squared plus r squared omega 4. Then from this you find out L. L becomes square root g squared plus r squared omega 4 over r omega squared, clear? Then you go for the answer, okay? Then you go for the answer, f equals gamma a x over L, you need to find x. What is the force? This is force m square root r squared omega 4 plus g squared. uh, F is this m r squared omega 4 g squared equals gamma into area length. What is length? This is the length, right? This is the length. This is the length. Gamma a. This is length. G squared. G squared plus r squared omega 4 over divided by r omega squared divided by r omega squared. Then you have x here. Then you have x here. Clear? Got the idea? Now it's a lot of work. You just solve for x, okay? You just solve for x. Clear? You just solve for x. So now you can do things, right? Now you can finish the question. What will be the answer for x? X will be, you take everything to this side and everything to this side. X is m. This multiplied by this. Both are same square root, right? R squared omega 4 g squared, yeah. So r squared omega 4 plus g squared m r squared omega 4 plus g squared over r omega squared over r omega squared into gamma a. This is the answer for x if you go in that path, okay? This is the answer for that question if you go in that path, okay? Clear? So ideally, like, because I can't remember like planning a question like that, okay? So I think ideally our plan in our mind was this, okay? Just a simple circle, okay? But the claim is entirely correct, okay? Claim is entirely correct. This is just for a horizontal circle, okay? That means someone is balancing the weight. Someone is balancing the weight, okay? Someone is balancing the weight. Ideally, it's on a table going in a circular motion, okay? Ideally, it's on a table going in a circular motion, okay? But ideally, if it is hanging, weight should do something. Weight should do something. So in that case, what happens is you have the weight downwards. In that case, you have the weight downwards, tension in this direction, F cos theta balancing the weight, F sin theta balancing the centripetal force. You multiply them at F squared cos squared theta plus F squared sin squared theta. This becomes 1. This is this side. You solve for F. Then you need to somehow find the length. You divide these two, get tan theta. From tan theta, you figure out sin theta. Sin theta equals from this 1 meter over length. From this side, from this one, sin theta is r omega squared over this. Then I solve for L. L becomes this. L becomes this. Then what I do is I have F equals gamma AX over L. Then what happens is here gamma A x, length of the string is this, taken using the sin theta, and the force in the string is this. You solve for that, you get that answer, and you can solve, right? Area is given, this is gamma, okay? My gamma and radius looks same, can't help, okay? This is gamma and that is r, okay? Work on that, okay? Work on that, you will feel the same issue, okay? Work on that. This is gamma. Area, gamma is given, Young's modulus given, area given, radius given 1 meter, omega given 1 revolutions per second, right? Is it minute or second? Second, right? That means 2 pi 2 pi radians per second, right? 1 revolutions per second means 1 revolution means 2 pi radians, right? So that means 2 pi radians per second, r given, g 10, everything else is given. So you find x, okay? Clear? Clear? That's correct. Okay, let's move a bit forward in theory. Okay, and thank you for this. Let's move a bit forward in theory. Okay, clear everyone? Clear? Okay. They don't usually give this kind of questions in A levels from this lesson, because these are the lessons that usually placed at the absolute end of the syllabus. So you can't give analytical questions from those areas. All you can do is asking simple questions, because ideally that's not happening now, because a lot of teachers finish this soon. But according to the plan in the syllabus, these are placed at the absolute end. Matter and radiation, this electronics. So they ideally give very simple questions in this area to make sure that students can handle that, because ideally they are learning it in the last moment at schools. So the exams are planned with schools. So ideally you learn these lessons in the last days of school. So you don't have enough time to do a lot of questions. So they just give surface level questions. Okay, you'll understand when we do past papers of this one. Clear everyone? Clear? Clear? Okay. So the important stuff in the syllabus is almost over. Okay. Important stuff in the syllabus is almost over. Anyone still writing this? Anyone? Anyone? Important stuff in the syllabus is over. Okay. But I have another bunch of content placed in your tute. Just for the sake of completion, that means they are not absolutely mentioned in the syllabus, but I have seen them asking this in a lot of past papers. Okay. That's why I have mentioned this. So I'm just going to roughly explain these things, because they are not ideally in the syllabus, but it's good to know. Okay. One is rubber, elasticity of rubber. Although I used rubber to explain elasticity, rubber is the worst example for that. Okay. Rubber is the worst example for that. Okay. Okay, rubber is not a good example for explaining elasticity, because rubber's elasticity curve will never look like this. Okay. Elasticity curve of rubber will never look like this. Okay. Clear? Elasticity curve of rubber will never look like this. Why? Why? The reason is, okay, the reason is, when you talk about rubber, okay, when you talk about rubber, what happens ideally is, rubber's behavior is entirely different. Rubber stretch too much, okay? Rubber stretch too much. It's not because rubber's Young's modulus is weak. Rubber stretch too much, but it's not because rubber's Young's modulus is weak. It's not the case. The scenario, the reason behind this is rubber's formation. You know, like, have you done that industrial chemistry part? Anyone? No? No? Not yet. I mean, rubber is made of carbon chains. Rubber is made of carbon chains like this. Okay. So when you stretch a rubber, what happens is its particles go far away. It's not its particles moving away from each other due to elasticity. It's not the case. What actually happens is, when you stretch it, okay, when you stretch this, okay, when you stretch this, what happens is, I mean, these carbon chains are like shrinked, right? These carbon chains are shrinked. When you stretch it, what happens is, it extends due to the slipping, and like, since these carbon chains are shrinked, I mean, now they are stretched and shrinked like this. When you pull it, it just try to go like this, and they stretch. Clear? Clear? Got the idea? Now the carbon chain is stretched. The carbon chains are going through each other and stretched like this. When you apply a force, the formation changes and they may try to extend. Then when you release, chains go back to the initial scenario. Then when you apply a force, chains become more relaxed and will increase the length. Clear? That's the formation of rubber. Okay, it's not particles going away from each other. It's the chains changing their formation. Clear? Chains slipping a bit, and shrinked chains gets more relaxed when you apply a force. Then when you release the force, they will again shrink like this. Clear? They will shrink like this. Got the idea? Got the idea? Okay. Now they are shrink. When you apply the force, they get relaxed and stretch. When you release it, they again go into each other. Clear? That's the reason for this extreme elasticity of rubber. Okay. So it's not because of weak Young's modulus. Okay. It's not due to a weak Young's modulus. It's due to the formation. Okay. So it doesn't actually follow the laws that we learned. Okay. It doesn't actually follow the laws we learned. There's no elastic region. Okay. It's entirely different. Okay. And one of the main nice properties, of rubber is, okay, one of the main and nice properties of rubber is if this is F and this is L, I mean, if this is force and this is extension, rubber will extend in one path and contract in a different path. That means it will extend like this. Okay. It will extend like this. Okay. When you apply a force, it will extend like this. Clear? That means what happens is its length increases with the force. So this is the work that I should do, right? This is the work done. This is the work done when we are increasing the length of a rubber, right? Or compressing a rubber. But when I release the force, it comes in a path like this. That means for the same extension, when you are applying the force is higher. When you releasing the force is lower. For the same extension, clear? For the same extension, when you are applying the force is higher. When you are releasing the force is lower. Clear? Force is lower. A kind of different scenario, okay? A kind of different scenario, okay? So the reason for this is, okay? So the reason for this behavior is, okay? I mean, definitely you may have felt this, right? When you extend a rubber, it's difficult, but when you are releasing, the forces are different. Okay? For a normal object, when you are applying the force, if the extension was 1 centimeter at 10 newtons, if the extension is 2 centimeter at 20 newtons, if you again reduce the force for 10 newtons, you will again get the extension of 1. That means the path you extend is equal to the path you return. Clear? If you apply 10 newtons to get a 1 centimeter extension, then you increase it to 20 newtons to get a 2 centimeter extension. When you release it again, when it falls to 10 newtons, it will return to 1 centimeter. Clear? The path you go is equal to the path you return. Clear? Path you go is equal to the path you return. Clear? But here, that's not the case. Path you go is different from the path you return. Clear? Clear? So this is the work done by the rubber when it returns. Okay? This is the work done by the rubber when it returns. Clear? Why am I talking about the work done? Why is that important? Why am I talking about the work done? The reason to talk about the work done is this. The story is like this. You stretch it, then you release it. Okay? Then in this case, then in this case, this property of rubber is really useful as a shock absorber. Okay, rubber is a very good shock absorber. That's why we have rubber tires, right? It will not transfer the shock to the vehicle. When you are going on a cart, you will feel everything that happens on the ground, right? The whole shock is returned to the cart because the cart wheel is wood. But in the vehicle, it does not happen. Okay, small stones here and there, small pits here and there. You don't feel that when you are going in a vehicle, right? With rubber tires. Why? What is the reason? This is the reason. Assume you are going in a vehicle. Now, the rubber tire feels some kind of a block like this. It goes through something like this. Now, what happens? It contracts. That means the change in length increases. It goes in a path like this. It goes in a path like this. Clear? The same scenario when it extend or when it contract. Okay, due to an external force. Clear? So when you apply, when due to this stone, it goes in a path like this. Clear? That means it stores a energy equal to this. Okay, it stores an energy like this. Clear? It stores an energy like this. Clear? Clear? It stores an energy like this. Okay, after storing this energy, after storing this energy after storing that energy, when you pass, that is the elastic potential energy stored due to this impact, that area. After this one, if this tire release that whole energy into the vehicle again, then having a tire is useless. It's just a delayed response, right? You will know that you fell for a pit after a second. That's all. You will feel the full impact, just like in a cart. Okay? You will feel that you pass the stone like this just after a second. Why? When you are going through this, you will absorb energy. Then when you pass it, you will release the full energy to the vehicle. Then no point of having a tire, right? You will feel everything felt by the tire just after few seconds. Just a delayed response, but you feel everything. Not a good way, right? Not a good thing, right? But the thing is, when it returns, it doesn't return in that path. It returns in another path with the smaller area. With a small area. That means the whole elastic energy it absorbs, it will not return. Clear? It absorbs an energy equal to this full area. When it returns a smaller area. Clear? The whole energy it absorbs, okay? The whole energy it absorbs, it will not return. Clear? Clear? It will return a smaller area. Okay? That means it absorbs the whole shock, a lot of potential, elastic potential energy, but it returns only part of that to the vehicle when it passes that block. What happens to the remaining area? What happens to the remaining area? What happens to the remaining area? Remaining area turns into heat by the rubber. When these carbon chains go through each other, slip on each other, it creates a lot of traction, lot of friction. It converts it into heat. Clear? So when you go through a block, you absorb it, but when returning, you don't return everything as kinetic energy. You return a smaller part as kinetic energy and you emit a lot as heat. That's why tires blow up when there's a lot of blocks and a lot of speed. Okay, when there's a lot of blocks and lot of speed, lot of issues. I mean, if when the tire has to face a lot of issues, that's why tires blow up sometimes. That's why tires heat up. Why? Tire is continuously converting energy into heat, so that you don't feel that. Okay, you don't feel that the elastic potential energy stored by this impulse will not entirely converted into kinetic energy and given to the vehicle. A lot of part will be converted into heat and only the remaining part will be felt by the vehicle. Clear? Clear? That's why Rubber is a perfect shock absorber. Clear? That's why rubber is a perfect shock absorber. Clear? Got the idea? Ah. So this is also not entire. This we call in the tube you have resilience of rubber. Convert it to hysteresis of rubber. It should be the perfect term. Hysteresis of rubber. Hysteresis of rubber. It should be the perfect term. Sinhala one is I think all right. It should be hysteresis of rubber. The term we give for that. Clear? Not entirely in the syllabus, but I have seen this graph they are giving in A levels, asking about the properties of rubber in the syllabus. Okay, so not entirely in the syllabus, but I have seen questions from that. Okay, so we can't neglect this part. Okay, we can't forget this part. Okay. Question. Okay. Some other factors related to this. Okay. Some other factors. These are also not entirely in the syllabus, but you have should have this slight idea. We only discuss or we do questions in the syllabus only in one dimensional changes. Okay. But there are thousands of other ways of deformation, and there are thousands of modulus given for that. Okay. That means for an example, this, if you have a, like, if you place a plastic box like this, if you place a plastic box like this, okay, if you place a plastic box like this, Okay. If you apply a force tangentially to this, okay, what will happen is it will incline a bit like this, right? It will incline a bit like this. Clear? Got the idea? Okay. It will incline by an angle of theta. Okay. So in a scenario like this, we define if this area is A, this tangential area is A, we define sigma stress as F over A and we define strain as theta. Clear? Strain as theta. Clear? In that scenario, the elastic modulus, we give the name rigidity modulus G equals sigma over R. Okay. I said that there are thousands of types of elastic modulus, right? When it is one dimensional, we call that Young's modulus. Now we call this rigidity modulus. Clear? Clear? In that case, sigma is F over A and strain is theta. Clear? Strain is theta. Clear? Okay? Strain is theta. Got the idea? So the diagram is not in the proper place. It's under bulk modulus. You should bring the diagram to the point where we talk about G, rigidity modulus. Okay? Diagram is slightly misplaced. Okay? Bring the diagram in the to the correct place. Just let me know like if there are any questions that I haven't answered yet, online students. I looked at them and I slightly try to answer them. So just mention them again in the chat if there are questions that I didn't answer yet. If there are questions that I didn't answer yet, just mention them in the chat again. Clear? These are not in the syllabus. Okay, so you may never see them. But in a essay paper, they may define a new sigma, new stress. They may define a new strain and they may give a question. Okay, I'm just teaching these stuff to show you that these kind of stuff exist. So if they give it in a essay paper, if they properly define, still you are not confused. Okay, 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 still you are not confused. Okay, elastic modulus is the common term. There are thousands of types of other modulus. Okay, under elastic modulus. Okay, another example, bulk modulus. Another example is bulk modulus. Okay, bulk modulus means you have a certain volume. You have a certain volume. You apply a certain pressure to that. You apply a certain pressure to that. Clear? You apply a certain pressure to that. Then it will reduce the volume, right? In a scenario like this, the pressure you apply is considered as strain. Pressure you apply considered as strain. Okay, and the change in volume divided by initial volume is considered as strain. Clear? Change in volume divided by initial length is considered as strain. In this case, elastic modulus, we give the name bulk modulus. We give the name bulk modulus equals stress over strain, here pressure over delta V over V. See? So don't like get the misconception of stress is always F over A, strain is always delta L over L. No. There are thousands of types of stress, thousands of type of strain. Okay? There are thousands of types of stress and strain. You just have to figure out the correct thing. Okay? Clear? Got the idea? Okay? But in our syllabus, you will only get questions from Young's modulus. But they always have the right to define these stuff and ask questions. Okay? And about rubber, they have asked questions. Okay? The way they ask questions about rubber is not they all of a sudden ask you why rubber is a shock absorber. You check past papers, they give you this diagram. Then ask why rubber acts as a shock absorber. It's impossible to think something like this in the time of A-level paper, right? Okay, they just give you the stress strain curve for rubber because it is not in the syllabus. Then they ask why rubber is a proper shock absorber. Okay, you can't entirely think this kind of stuff in the A-level time, right? Okay, okay. So that's why I'm mentioning them. Otherwise, they are not entirely properly defined in the syllabus. Okay, clear? So that's all. Okay, so the last 2 pages that I explained are not actually in the syllabus, but it's good to know. Okay, practicals, let's keep for the end. Let's go for viscosity. But before going for viscosity, I'll answer the questions remaining from physical students and online students. So you need to cover waves and oscillations. Just request for the recordings, okay? I send you the number. Send a request for the recordings. Just send the message to me. Expansion part in the sense, the question related to the tire, question related to the wheel, or the just that equation, gamma, okay, theory part, okay. That's all right. That's the only question that I haven't answered yet, right? Okay, that I'll do. Others from the physical class, any questions? You need me to explain anything again? Anyways, finish the all the exercises, okay? After the lesson, I'll do some question sessions to finish the exercises. Any questions other than that? So the plan is I'll take 5 minutes and explain that expansion thing again. Then let's move to viscosity. So this one, what I need to find is what happens if you place something inside a block like this. Okay, in a building, you have something in between like this, a beam. You increase the temperature. When you increase the temperature, this beam tries to expand, but these two sides, walls are stopping that. Due to that, a compressive force will occur between the beam and the compressive force will occur between the beam and the wall. That compressive force I need to find. That compressive force I need to find. For that, I will apply this equation, the usual equation gamma A x over L. But what I would do is, I will take this out. Then I will first increase the temperature, then I will get this length. Now what is actually happening is a beam of this length, I shrink it and put it here, right? Beam of this length, I actually shrink it and put it here, clear? Beam of this length, I shrink it and put it here, clear? Clear? So in this case, okay, in this case, gamma A x over L, so I write gamma A. What is x? X is this difference, right? X is this difference. Object of this length, now I shrink and put back in. Clear? Clear? So the difference would be L plus L alpha theta minus original length L. So you get L alpha theta. So that is x. Clear? And what is the initial length of the object? This is the initial length of the object. The way I do it, I take it out, I increase the temperature, that acts as the initial length, and I shrink it by this length and I put it here. So the change in length is this. Then L and L cancels out, you have gamma A alpha theta 1 plus alpha theta. Then what you do is 1 plus alpha theta, it's just a trouble to keep it here. But you know that in a construction or like in fields like this, we don't talk about increasing the temperature by 100 Celsius, right? walls and beams, these kind of scenarios occurs practically in buildings kind of stuff, right? So the temperature does not increase by 100 Celsius in a scenario like this, right? It never increase by 1000 Celsius, okay? It will be just few degrees. And alpha is usually linear expansion of objects is 10 to the power minus 5, 10 to the power minus 3, 10 to the power minus 4, like that, right? Expansivities are really small. So this alpha theta is a really small value. So 1 plus alpha theta I can write as 1, right? It's okay to write 1 plus alpha theta. That means 1 plus a really small value is almost equal to 1, right? So I can write it as 1, which will give me gamma A alpha theta. So if you get a question in this area, it's quite easy. You put the Young's modulus here, area here, linear expansivity here, temperature difference here, you get the answer. Clear? Clear? That's all. Got the idea? Clear, everyone? Okay. Let's move to the next topic. You try the questions as homework and ask me the required question numbers. Inform me the required question numbers next week, okay? In the class. So let's move to the next part. Viscosity. Viscosity. What is viscosity? What is viscosity? It is like this, okay? If you are swimming in water, or if you take your hand through water, you feel a certain friction, right? You definitely feel a certain friction, right? Clear? You definitely feel a certain friction, okay? So the scenario is this. Definitely water or any liquid creates a friction, right? Creates a friction. That friction we call viscous force, and that friction force we analyze in viscosity lesson. Clear? Friction forces in liquids, okay? So if we analyze, first before moving to viscosity, we have to analyze the types of liquids, how liquids flow, some special terms related to liquids. We have to first finish those areas before moving into before understanding viscosity and viscous forces, okay? So there are two main types of flow. One is turbulent and other one is streamline. You already know this through mechanics, right? Turbulent means the liquid is not going in a very orderly manner. It has a rotational motion, it has a linear motion, it has a bunch of types of other motions, okay? It's not going in a orderly manner, it's going really fast and it's not going neatly. Clear? And in Bernoulli, you learn the streamline flow, anakula tarala. Streamline flow. Clear? What is streamline flow? Anakula tarala kiyanne? They goes in a order. They goes in a order. It does not change. It is very static. That means if you keep looking at this place, every particle that pass this place will have the same velocity. Every particle that pass this point will have the same velocity. Clear? And they will have a linear velocity only. They don't have rotational motions. Okay? Then they together create stream tubes. They together create stream tubes. When you consider a stream tube, the liquid don't flow out, liquid don't flow in. Same volume continues to flow as a stream tube. Clear? Same volume continues to flow as a stream tube. Clear? Can you remember these properties from Bernoulli's law? When we were learning Bernoulli's law and continuity equation, A1 V1 equals A2 V2. We analyzed streamline flow, right? So this is a streamline flow, okay? But again, we know that there's something called critical velocity, avadhi pravegya. What is critical velocity? Critical velocity is the velocity at which the liquid turns from streamline to turbulent. If a liquid goes really fast, it can't be streamlined, it will turn turbulent, okay? Critical velocity means the maximum velocity that you can stay streamlined, okay? Critical velocity is the maximum velocity that you can stay streamlined, okay? After that, you will become turbulent, clear? After that, the liquid will become turbulent. Got the idea? Clear? Ah. So in this case, okay, in this case, uh, one of the main types of flow we analyze in this viscosity lesson is laminar flow. It's a property of streamline flow. Usually laminar flow is almost, streamline flow is usually laminar. But here, what is a proper laminar flow is, these are the main two topics that we analyze, right? Streamline and turbulent, clear? Then what one of the main topics, okay? One of the main topics related to like in for viscosity lesson is a laminar flow. A laminar flow is a flow that goes as a streamline flow, but it properly travels as layers. It properly travels as layers. That means all the particles in the first layer will have the same velocity. All the particles in the first layer will have the same velocity. The layer below will have a different velocity, but all the particles in that layer have the same velocity. You go to the next layer, it will have a different velocity, but all the particles in that layer will have the same velocity. Clear? In streamline, we are talking about one point. We are looking at one point and that point has the same velocity. But in lamina, they should go in a layered manner. Okay, you have the first layer going in a certain velocity, next layer going in a certain velocity, the next layer going in a certain velocity, okay? It behaves as layers, okay? Lot of practical, I mean, when a river flows slowly, it's a laminar flow, okay? When liquids are not disturbed, when they are flowing peacefully, they always go in a laminar flow, okay? Clear? When the liquids, okay? When the liquids travel peacefully, okay, without a lot of turbulence, it is a it acts as a laminar flow. Clear? So the story is this, okay? The story is this. Now, is everything clear up to this point? Is everything okay up to this point? Yeah. So when something is going as a laminar flow, then we can talk about viscosity properly. That means even in turbulent flows, you have viscosity, okay? But the problem is you can't quantify that viscosity, okay? You can't you can't create equations for that. But for laminar flow, you can create equations, clear? For laminar flow, we can create equations, okay? So what are the equations? The first one is, as usual, Newton figured out an equation, okay? So the equation is Newton's law of viscosity. What is Newton's law of viscosity? Before that, we have to learn another term called velocity gradient. If you take a river, if it flows as a, if this is the ground of the river, if it flows as a laminar flow, that means if it flows as layers, lowest layer which touch the ground, lowest layer that touch the ground will have the same velocity as the ground, okay? It will have the same velocity as the ground, which is 0. There will be a layer that is in contact with the river, ground. Ground is stationary. So there will be a layer that is stationary. Okay, that is stationary, that is in contact with the ground. Okay, that means when a laminar flow meets a solid object, it gets the velocity of that solid object because it bonds with that solid object. Clear? But the highest layer of the river will have a good velocity. That's how the rivers flow. So definitely from here to here, velocity changes from here to here. Velocity changes accordingly like this. Clear? From here to here, velocity changes accordingly like this. Clear? Clear? This velocity is 0. This has a higher velocity. Clear? This velocity is 0 and this has a higher velocity. Clear? Then, if this length is h or delta h, okay, if the velocity difference from here to here is delta v, the velocity gradient is delta v over delta h. Clear? Velocity gradient is delta v over delta h. Clear? Change in velocity over change in distance. That means how much the velocity changes with the distance. Clear? How much the velocity changes with the distance. That means delta v over delta h. Clear? Delta v over delta h. This is velocity gradient, and what Newton said was, if this is a liquid layer, now since they are moving as layers, there's a relative velocity between layers, right? Since this is moving as layers, definitely there's a relative velocity between layers, right? Clear? So if there's a relative velocity between layers, okay, if there's a relative velocity between layers, a friction force may occur between these layers, okay? Friction force may occur between these layers. That friction force we are trying to find. Clear? That is viscous force, okay? Since it is moving as layers, and since layers have different velocities, there's a relative motion between layers, and the friction force may occur between these layers, and that friction force I'm going to find, okay? So Newton said the friction force acting over a unit area, that means F over A. The friction force that acts over a unit area. Clear? F over A. Friction over area. Friction force acting on a unit area is proportional to the velocity gradient of that system. Clear? That is Newton's law. Clear? Friction force acting on a unit area is proportional to the velocity gradient. Clear? Clear? And the proportionality constant here is neta. Proportionality constant here is neta. We call that viscous coefficient. Clear? Viscous coefficient of a liquid. It depends on the liquid. Clear? Got the idea? So you can find the friction force by neta A delta V over delta H. Got the idea? Clear? This is the equation. This is the first equation. This is Newton's law of viscosity. Clear? Go to exercise 2. Go to exercise 2. Try question 1. Try question 1 and question 10. Try question 1 and 10. Exercise 2, question 1. Exercise 2, question 1. A layer of oil of thickness D is placed on a horizontal flat surface. A rectangular piece of wood of mass M is placed. The area of the bottom of the block is A, and the viscosity coefficient of oil is neta. It moves because at P force is applied along the surface on the block of wood. In the fourth one of this, it's not clear, right? Only the fourth one is not clear. Find its velocity as the block of wood accelerates. Just mention that in the fourth one you have to find the velocity of the block when the wood does not accelerate. In the fourth part of the question, velocity of the block when the wood does not accelerate. So the question is quite simple. You have something like this rectangular piece of wood of mass m, mass is m, area of the bottom of the block is A, viscous coefficient of oil is neta, viscous coefficient of oil is neta. It moves because a P force is applied along the surface on the block of wood. So we apply a P force on this, and it's on a oil layer. It's on a layer of oil, and the layer of oil, the thickness of oil is D. Thickness of oil is D. I'll just draw it like this. Thickness of oil is D. Thickness of oil is D. And this is the ground floor. Mass of the wood is M. Okay. At the moment when the velocity of the wooden block is V, find the viscosity force acting by the oil against the motion. Find the viscosity force acting by the oil against the motion. So now the velocity of the block is V. Now this is the idea. So when a liquid layer is bond with a solid surface, it takes the velocity of the solid, right? That means here it's ground, so the velocity is 0. Clear? Here it's the velocity of this wood, which is V. Clear? So the velocity gradient delta V over delta H. Velocity gradient is here the velocity is V, here it is 0, V minus 0, V minus 0, here it is D. V minus 0 over D. Clear? It is V minus 0 over D. Clear? Clear? V minus 0 over D, which gives us V over D. Which gives us V over D. Clear? Clear? Huh. Then what I can do is, area is also A. Area is also given as A. So I can apply Newton's law. F over A equals neta delta V over delta H. So I get F equals, I'll take A there, neta A delta V over delta H. Velocity gradient is V over D. This is the friction force felt by the wood. Clear? This is the friction force felt by the wood. Clear? Clear? Then the next one. Then the next one. Obtain an expression if the, this is question 1, right? Obtain an expression if the acceleration at the moment the velocity v is a. So get an expression for the acceleration. So you take this wood. The friction force is given by this. So this is the friction force, right? This is the friction force. And you are applying a force of P. You are applying a force of P. Clear? You are applying a force of P. Clear? Then you apply F equals ma. Okay? Then you apply F equals ma in this direction. So it is P minus friction. It is P minus friction equals ma. Then the acceleration is P minus friction is this, right? This is friction, clear? Neta AV over D. Neta AV over D, P minus friction over M. P minus friction over M. This is the acceleration, clear? This is the acceleration, clear? Then find the velocity as the block of wood accelerates. The fourth one I asked you to change. When the block of wood is not accelerating, that means when the acceleration is 0. When the acceleration is 0, this part is 0. P minus neta AV over D is 0. That means when the velocity of the wood is P D over neta A, then acceleration will be 0, clear? That means when the force you are applying is entirely equal to the friction, when the force you are applying is entirely equal to the friction, then it will not move, clear? When the force you are applying is entirely equal to the friction, then it will not move, then it will not accelerate, sorry, clear? That is the maximum acceleration, right? Sorry, the third one, sorry, I missed the third one. Is this clear? Fourth one? Okay, when you are applying the force P, when it is equal to the friction, okay? When the friction is equal to P, that means when these two are equal, then it will not accelerate anymore, clear? Then it will not accelerate anymore, clear? Then I'll do the third one. I have missed the third one. Third one is quite simple. Uh, third one is, uh, in the third one what you have is this. What is the maximum acceleration, right? So maximum acceleration is definitely F equals ma, P equals ma. So the maximum acceleration is P of m, right? That means when you start moving this, there is no velocity, right? At the beginning there's no velocity, right? When you start moving this, there's no velocity, right? Clear? There's no velocity when you start moving this, clear? So if there is no velocity when you start moving this, clear? Then you will feel the same, like, sorry, I mean, at the beginning of the motion, there's only P force acting, no friction. So the same force will act as the overall force, right? Same force P will act as the overall force, right? At the beginning of motion. So F equals ma, P equals ma, maximum acceleration is P of m, clear? Write down things up to this point. Then let's move to graphs. Draw the graphs now. Now you have a slight understanding, I think. Now draw the graphs related to these scenarios. Acceleration, velocity, and displacement graphs. So hope no questions up to this point. Okay. Then what will be the behavior of the graphs? Quite simple. What about the acceleration? What about the acceleration? At the beginning, you have the maximum acceleration P of m. Then with the acceleration, velocity increases. With the acceleration, velocity increases. Clear? When velocity increases, what happens? Acceleration decreases. See? When velocity increases, acceleration decreases, right? Clear? Acceleration keeps decreasing and reach to zero at a certain point. Clear? Clear? Okay. Acceleration keeps decreasing and reach to zero at a certain velocity, right? At a certain velocity, these two becomes equal and acceleration reach to zero. Clear? Then if I draw the behavior of velocity, see, if I draw the behavior of velocity, velocity will always increase. Why? See, acceleration is always positive. See, acceleration is always positive. Clear? So, velocity will always increase. But what happens to the gradient? See, acceleration decreases, that means positive gradient decreases, right? Acceleration decreases, that means positive gradient decreases. Clear? Acceleration decreases to zero, that means positive gradient decreases. Clear? Positive gradient decreases and it reach to zero. Gradient reach to zero. Acceleration going to zero means gradient going to zero, right? Whatever happens to the acceleration happens to the gradient of the velocity time graph. Then what about the displacement time graphs? What about the displacement time graph? Displacement will continuously increase. Okay. Whatever happens to this happens to the gradient of this guy, right? So velocity increases, that means gradient increases. Velocity increases, that means gradient increases. Clear? But now velocity becomes constant, that means here gradient becomes a constant. Clear? Here velocity becomes a constant, that means gradient becomes a constant. Got the idea? Let's go to question 10. Let's go to question 10. Okay. So the 10th question is also not that difficult, right? 10th question, question 10. This is the setup. 30 here. There's a block of wood like this. There's a block of wood like this. Uh, Glass plate measuring 5 centimeters and 2 centimeters. In the diagram, there's 50 centimeters mentioned. I think it should be a mistake, right? Yes, right? Did you take 5 or 50? Anyways, the question is not that difficult, so you don't have to fuss about that. Uh, the idea is quite simple. Uh, this is the weight downward. This is the weight downward, okay? And the weight will have a component in this direction, okay? Weight will have a component in this direction. What is that? mg sine 30. mg sine 30. Clear? mg sine 30. Clear? So definitely, why is this balanced? Why is this? It's moving in under constant velocity, right? Why is that? The friction force is balancing the weight component, right? Friction force is balancing the weight component, clear? And what is friction force? Neta A delta V over delta H, clear? Friction force is equal to the downward force component, clear? Clear? So you write M. What is M? What is the mass of the object? Do we have that? Don't we have the mass? No? Okay, it's a problem. Uh, they have to mass. I have to determine the mass of the glass plate. I mean, I just read the question roughly. Okay, just mention if I'm doing something wrong. I mean, I'm too lazy to read the whole question. Okay, I mean, luckily we got a very difficult paper in 2019. Otherwise, I'm not in University of Morocco. Okay, because I mean, I just don't read the question properly. I just roughly see the question here and there, and I do something, and I get the answer. Okay, that's how I was, and that's how I am. Uh, but the last days, towards the last days of A level, I worked a lot on that. I have mentioned you methods, right? I have mentioned you specific methods to get rid of careless mistakes. Otherwise, I just read the question roughly. Go for answers. I got like 46, 47 MCQs for physics. It was huge in 2019 paper. So luckily, we got an extremely difficult physics paper. Otherwise, I'm not in the university. Okay. So so just let me know, okay, if I'm in the correct wrong path. I never read the question properly. I just go through the question roughly and assume what they're asking and try to do something. Okay, which is not good. Don't do that. Okay. So they need us to find the mass, right? So mg sine 30 downwards, mg sine 30 downwards equals neta a delta v over delta h. Delta v over delta h. Clear? And that year, 2019, lot of people like that went to the universities, okay? Lot of people like that went to the university. Like purely by physics. No careless mistakes involved. No one have to care about careless mistakes because no one wrote the papers properly. So you just do the paper. It's quite easy when the papers are difficult. So mg sine 30 downward equals neta a delta v over delta h. Clear? So you have m we have to find g10 sine 30 half equals neta a delta v over delta h. So what is neta? 2.42. 2.42. Area, someone can take 50 into 2 or 5 into 2. I'll take 5 into 2 area. Area 5 into 2. It's given in the text. 10 to the power minus 4. 10 to the power minus 4. And delta v over delta h is, what is the velocity here? What is the velocity of this block? 1 centimeters per second, right? and here it is 0, right? So the velocity difference, what is the velocity difference? 1 minus 0, 1 into 10 to the power minus 2, 1 centimeters per second minus 0 over distance. Over distance is this. This is the thickness. This is the thickness. What is the thickness? What is the thickness? 0.5, right? 0.5 millimeters. 0.5 millimeters. 0.5 millimeters. 0.5 millimeters. This is the answer, clear? But in actually in university exams and even in A levels, I don't think that I made a lot of careless mistakes because I'm really careful about that because I know how I am. So I mean, I have specific methods. I worked on that a lot. So when I'm doing a paper, I'm an entirely different person. Okay, I'm really focused. I read the question from beginning to end properly. I have specific methods to keep the focus because those are the kind of stuff I find difficult. So I'm good at that when I'm doing papers. Okay, that's why I'm performing really well in university exams. Because you have to be really careful in university exams. No one cares about giving marks for the method. Okay, professors have more than enough work to do. Okay, you have the answer, you get 100. You don't have the answer, you get 0. Okay, so in COVID period, there was one paper was given. Those days papers were given online. Everyone in the class will get a different question. Okay, for one full module, 100 marks. One full module, 100 marks. A huge question, 2 pages, and thousands of calculations, double integrations, vector calculations, thousands of calculations. And at the end of the whole question, you have a small square to fill. You type the answer here, automatically checked. If you get the correct answer, pass. If you get the wrong answer, fail. No A, B, C, D. I mean, there's a proper set of like marks you get. You either get A plus, A minus, B plus, like that, like that. Then you fail. Okay. So there's a bunch of results. No. Okay. No one questions lecturers in the university. They do whatever they need. Okay. So you either pass or you either repeat. Okay. Okay. And only one square to fill after thousands of vector calculations. Okay, there's millions of places where you can get things wrong. Okay, okay, like it is the question is like the size of like 10 times the size of your pure maths paper. Okay, okay, and like 100 times difficult calculations, and at the end of the whole question the guy is so lazy to check the method and all, so automatically marked answer box is there. You type the answer, you press enter. Either you pass, either you repeat. Okay. So you have to be really careful when doing university exams. But I mean, I'm really careful. I mean, I'm a different person there because I'm not good at that. Okay. I'm not good at that. I'm not a careful person. So when I'm doing a paper, I specifically change my personality. I specifically change the way I do things. I specifically implement methods to get rid of careless mistakes. I do a lot of stuff to get rid of the issues that I have. So I think I write papers really well. Okay, that's why I get very good marks in university by investing a very low time. Okay, I mean now we have the convocation on December. I think I'm in top 3 batch, definitely 1 or 2 or 3. But I have gone to university. I mean my attendance is like 15%, 10%, 5% for all the semesters. Okay, no attendance, and I'm not that intelligent compared to university. I mean, you don't feel intelligent when you are in University of Moratu, okay? Because everyone is intelligent. So no one cares, okay? No one cares about intelligence. You have to be careful. So I perform very well in university exams because I'm specifically careful when I'm writing a paper because I'm really careless in real life. Okay. I mean, I can't waste my brain capacity to read this properly. See the length of that. So but when I'm doing a paper, I specifically know that. I usually do that. I don't read the paper. I know that. So I specifically check whether I read the paper from beginning to end. I even do that. Okay. I do a lot of stuff. So you just figure out your issues, then implement methods for that. Okay. Don't do what everyone else is doing. Okay. One small theory concept and I'll finish. Okay. One small theory concept and I'll finish. Like, this is the story. Uh, Now again, when a when a liquid flows in a huge tube, okay, or a river, then this issue doesn't matter, okay. Water goes like this when it is going in a huge tube, okay. But when a liquid travels in a smaller tube, maybe in a tree, or maybe in a cylinder, maybe from a, in the line, okay. When liquid travels in a smaller tube inside a vehicle, okay, okay, in AC systems, okay, when liquids travel in a very small tube, definitely again viscosity matters, okay, definitely again viscosity matters. When it is going in a huge pipe like this, it just flows, okay, viscosity doesn't matter a lot, okay. But when it is going in a small tube, okay, viscosity matters a lot, okay, viscosity matters a lot. So in a scenario like this, if this is flat, how does the liquid go from here to here? Due to the pressure difference, okay? Due to the pressure difference. Clear? Clear? So definitely, if we need to find the fluid flow rate, that means how fast the fluid travels through this, okay? If you need to figure out how fast the fluid travels through this, I'll get delta Q over delta T. That means how fast the fluid travels, volume flow rate, volume over time, okay? Definitely, this depends on the pressure difference, okay? Definitely, this depends on the pressure difference, okay? But it depends on not only the pressure difference over length. How much of a pressure difference for a given length, okay? This P2 minus P1 over L, pressure difference over length, we call delta P over delta L, the pressure gradient. This is a new term, okay? Delta P over delta L, we call this the pressure gradient, okay? Clear? Pressure gradient, delta P over delta L. Clear? Pressure difference P2 minus P1 over length. We call that delta P over delta L, pressure gradient. Clear? So definitely how fast liquid travels through this entirely depends on the pressure gradient. Delta P over delta L. Clear? It entirely depends on the pressure gradient. Okay? Then the next thing is definitely it depends on the viscous coefficient. Okay? Now the layers are going like with like together, right? So definitely viscosity matters, and definitely the area matters, right? Definitely the area matters, but we write it as the radius. We consider that the radius matters because it is a tube. Radius represents the area, right? So we need to create a relationship between this and these three. Okay, we need to create a relationship between this and these three. For that we use dimensional analysis. Okay, I'm not going to do that part, it is included in the tute. We use dimensional analysis to create a relationship. After applying dimensional analysis, we get delta Q over delta T is proportional to R to the power 4 neta delta P over delta L. After dimensional analysis, clear? Sorry, R to the power 4 over neta, sorry. Clear? Clear? Then when I experimentally find the proportionality constant, I get delta Q over delta T equals pi over 8 R to the power 4 over neta delta P over delta L. Pi over 8 R to the power 4 over neta delta P over delta L. This we call Poiseuille's law. Pressure difference over length R to the power 4 over neta pi over 8 gives you how fast the liquid travels through a tube. We call that the volume flow rate. Clear? Volume flow rate. Clear? Okay. How fast the liquid travels through the tube. You call it the volume flow rate. Clear? Volume flow rate. Okay. Uh, so this is Poisson's law. Okay, we are not going to do a lot of work based on Poisson's law. I'll do that next week. I have a few, like 1 or 2 points to mention before like finishing the class today. Uh, is this clear? Okay, if you like, you can try questions, but next week only we are starting to do Poisson's equation questions. Okay, but to apply Poisson's law, okay, to apply Poisson's law, there are a bunch of requirements. Okay, one is the liquid should be streamlined. Okay, when the liquid is going really fast, when it is turbulent, this doesn't work anymore. Okay, there's a huge kinetic energy and the liquid would jump out. You don't have an orderly manner. Okay, so definitely this works when the liquid is streamlined. Okay, clear? Then again, liquid should be incompressible, so this can't be applied to gas. Why? We assume that in this case, we assume that pressure difference drives the liquid, right? Or the problem is, if it is compressible, a liquid that gets compressed, by the pressure, volume will decrease instead of flowing, right? By this pressure difference, if it is a gas, if it is a compressible liquid, the volume may decrease, right? Instead of moving out. Clear? So the liquid should be incompressible. Any liquid is considered incompressible usually. But the problem is in many questions, even in Bernoulli's, we consider gas as a liquid when we are doing questions, right? But the problem is for gas, this doesn't work, okay? For gas, this doesn't work. Clear? Okay. Then other things are, this should be a thin tube, okay? For a huge tube, this doesn't work, okay? Okay, clear? Then the liquid should go in a steady condition. You can't change the system time to time, clear? Okay, there are conditions to apply Poisson's law, okay? And at the same time, ideally, the tube should be flat, okay? That is not a mandatory requirement, but ideally it is good to have this condition. Why? Otherwise, the weight of the liquid will support to flow, right? Otherwise, the weight of the liquid will support the flow a bit, right? Otherwise, the weight of the liquid will support the flow a bit. Clear? Clear? Ah. So, this is the idea. Clear? Okay. Ah. Then we are not going to do questions in Poisson's today, but there are some stuff to mention. Both, otherwise I will forget these stuff. That's why. Both the viscous coefficient and Young's modulus decreases with temperature. Okay. Both viscous coefficient and Young's modulus decreases with temperature. Okay. That's why we heat things up if we need to change its shape. That's why we heat things up if we need to change its shape. Both Young's modulus and viscous coefficient decreases with the temperature. Okay. Then again, one more thing. I mean, the theory is over for today. I'm just mentioning some theory parts that I think that I should mention. And another thing is, like you have the sigma and epsilon graph, stress strain curve. Okay. Be careful. 1 year they asked this. That's why now I have mentioned it in the tute. 1 year they asked you to draw this. Okay, people just draw whatever they like, but they have shifted this. Okay, nobody learned it that way. Okay, so the graph would look like this. Okay, that's why now I have included in the tute. 1 year in A levels they asked this. Okay, instead of this. Okay, students just study the shape. In A levels, some people can't even figure out what is the difference between these two. Okay, see, axis is changed. That's why I have included in the tute. Okay, otherwise there's no point of learning that. It's the same graph, axis interchanged. Then again, if someone asks you instead of this graph, fx graph, you will get the same shape, right? Why? Sigma is f over area and this is x over initial length, okay? Clear? So force is sigma into area and area is a constant for a given system, right? So you are just multiplying this axis by a constant. Then x is strain into length. Okay, again, length is a constant for a given system, right? So we are just multiplying this axis and this axis by two constants, okay? We are multiplying this axis and this axis by two constants, clear? So the graph will sometimes stretch a bit, would go up a bit, scale may change a bit, but you will have the same shape, okay? You will have the same shape, okay? Clear? Okay, so yep. So that's all for today. Try to finish exercise 2, but there are Poisson's equation questions. I'm not asking you to do them, but if possible, try them. If possible, try them. Let's next week we'll be able to finish theory, but I can't guarantee that next week we'll be able to finish questions too. Then let's figure out a plan for that next week. But for theory, next week we can finish. Okay. Okay. So let's try to like try to finish until the end of exercise 2. Then let's quickly discuss questions next week. Then move to the other theory parts. Okay. Thank you.